Hello there, and welcome to Science for Sleep, a quiet little corner where curiosity slows down, explanations take their time, and the universe becomes something you can gently explore while the rest of the world grows quiet. Tonight we're going to spend a while looking up, in a sense. Not in the rushed, neck-craning way we sometimes glance at the night sky on a cold evening, but slowly, thoughtfully, the way humans have done for thousands of years when they had nowhere else to be except under the stars. Our topic tonight centres on a single point of light that most people have heard about at least once in their lives. A star that has been used by travellers, sailors, explorers, astronomers, and curious night watchers for centuries. A star that sits quietly above the northern half of our planet and appears to hold the entire sky in place. That star is Polaris. You might know it by another name, the North Star. But here is something interesting right away. The reason Polaris matters so much has very little to do with how bright it is, or how large it is, or even how unusual it is as a star. In fact, there are thousands of stars in the sky that are brighter, larger, and more energetic. Yet Polaris became one of the most important stars humans have ever known. And the reason has everything to do with physics. Before we dive into that though, let me ask you something small and personal. The kind of question that quietly connects all of us who happen to be listening to the same story at different moments across the planet. Where are you listening from tonight? Are you somewhere in the northern hemisphere where Polaris is actually visible above the horizon? Maybe you're in a city where the sky glows faintly orange with streetlights. Or maybe you're somewhere darker where the Milky Way can still stretch overhead like a pale river of light. And what time is it where you are right now? It's a slightly fitting question when the subject involves the sky and the slow movements of Earth, because the exact position of the stars above you depends entirely on where and when you happen to be listening. Two people on opposite sides of the planet can look upward at the same moment and see completely different skies. Still, if they are both somewhere north of the equator, there is one thing they will share: Polaris. If you find this kind of slow exploration soothing, or if it helps your mind gently drift away from the noise of the day, consider giving the video a like and maybe subscribing to the channel. It helps this quiet project reach other curious minds who might also enjoy falling asleep somewhere between astronomy and physics. Now, with that said, let's begin with something very simple. Imagine stepping outside late at night. The air is cool, the ground is still, and above you the sky stretches in every direction. At first glance, the stars might seem scattered randomly, like tiny grains of light tossed across a dark surface. But if you stay outside long enough, something curious begins to happen. The sky starts to move, not quickly of course. The motion is so slow that you rarely notice it unless you watch carefully or compare the stars to something fixed on the ground like a rooftop or a tree branch. But hour by hour the stars drift across the sky in wide sweeping arcs. They rise in the east, they climb across the night, and eventually they sink in the west. This steady motion is so reliable that ancient civilizations used it to measure time long before mechanical clocks ever existed. The sky itself became a giant rotating map. Now, here is the part that becomes especially interesting once you pay attention long enough. Most stars follow large circular paths across the sky, but one star behaves differently. Near the northern horizon, there is a point around which the entire sky seems to rotate. The stars trace huge circles centered on that location, like sparks spinning around a slowly turning wheel. And very close to the center of that wheel sits Polaris. If you watch the sky for many hours, every other star would move noticeably. Some would climb higher, others would sink lower. Constellations would rotate and drift across the darkness. Yet Polaris would barely shift at all. It would remain almost perfectly fixed. To early observers, this must have seemed almost magical. A sky that constantly turns, and a single star that refuses to move with the rest. But once physics enters the picture, the explanation becomes both simpler and more fascinating at the same time. The motion of the stars across the sky has nothing to do with the stars themselves moving rapidly around Earth. Instead, it happens because Earth is rotating. Our planet spins once every 24 hours. We rarely feel that rotation because everything around us, the air, the ground, the oceans, and our own bodies, rotates together with the planet. From our perspective on the surface, it feels as though the ground is perfectly still. But the sky reveals the truth. As Earth turns, our viewpoint slowly changes, and that makes the stars appear to move across the sky from east to west. This effect is very similar to what happens if you sit in a slowly rotating chair while looking at objects around the room. The objects themselves do not move, yet your changing position makes them appear to circle around you. The night sky works the same way. Every star in the sky appears to move in a circular path because Earth is spinning beneath them. But those circles all share a common centre. That centre is the direction in space that Earth's rotational axis points toward, and at the moment that direction lies extremely close to Polaris. This point in the sky is called the North Celestial Pole. You can think of it as the projection of Earth's axis into space. If you could extend an imaginary line from the North Pole straight outward into the universe, it would point almost directly at Polaris. Because of this alignment, Polaris sits nearly at the centre of the circular motion created by Earth's rotation. Stars farther away from that centre trace wide arcs across the sky. Stars closer to it trace smaller circles. And Polaris, sitting very near the exact centre, appears almost perfectly stationary. The entire sky seems to rotate around it. That simple geometric relationship turned Polaris into something extraordinarily useful. For travellers and navigators in the Northern Hemisphere, Polaris became a natural compass point in the sky. No matter where you stood, if you could locate Polaris, you instantly knew which direction was north. Long before magnetic compasses became common, the sky itself provided orientation. But Polaris offered something even more powerful than direction. It could tell you where you were on Earth. To understand how that works, picture the surface of our planet as a giant sphere. Locations on that sphere are described using latitude, which measures how far north or south you are from the equator. At the equator, latitude is 0 degrees. At the North Pole, latitude is 90 degrees north. Now imagine standing somewhere in the Northern Hemisphere and looking up at Polaris. The angle between Polaris and the horizon turns out to match your latitude almost exactly. If Polaris appears 30 degrees above the horizon, you're roughly at 30 degrees north latitude. If Polaris appears 50 degrees above the horizon, you're near 50 degrees north. This happens because of the same geometry that links Polaris to Earth's axis. The farther north you travel, the more directly you face that axis in space, and the higher Polaris climbs in the sky. At the North Pole itself, Polaris would appear almost directly overhead. At the equator, Polaris would sit right on the horizon. South of the equator, it disappears entirely below the curve of Earth. For centuries, sailors crossing open oceans used this simple measurement to determine their position on the planet. By measuring the angle of Polaris above the horizon, using instruments like sextants or astrolabes, navigators could estimate their latitude with remarkable accuracy. A single star became a geographic tool, and that is where the deeper physics quietly hides beneath the practical usefulness. Because Polaris itself is not truly fixed in space. It only appears that way from our current perspective on Earth. In reality, Polaris is just another star moving through the galaxy like billions of others. It lies roughly 430 light-years away from us, which means the light reaching your eyes tonight began its journey during the early 17th century. At that distance, even enormous motions in space appear extremely slow when viewed from Earth. But there is another, more subtle reason Polaris occupies its special position. Earth's axis does not point in the same direction forever. Over very long periods of time, the orientation of our planet slowly shifts. The axis traces a gentle circle in space, a motion caused primarily by gravitational interactions between Earth, the Moon, and the Sun. This slow change is called axial precession. The movement is incredibly gradual. One complete cycle takes about 26,000 years. Because of this wobble, the direction of Earth's axis slowly drifts across the sky. Thousands of years ago, Polaris was not the North Star. Thousands of years from now, it will no longer hold that role. Different stars take turns occupying that position, as Earth's axis slowly sweeps through space. At the moment in history when you happen to be alive, Polaris sits conveniently close to the North Celestial Pole. But this is only temporary on cosmic timescales. Ancient Egyptian astronomers, for example, lived during a period when a different star named Thuban in the constellation Draco was much closer to the North Celestial Pole than Polaris is today. Their pyramids were aligned using a slightly different guide star. Thousands of years in the future, yet another star will inherit the title. Still, for our current era, Polaris serves as the most stable point in the northern sky. That stability turned it into one of humanity's most reliable astronomical references. And the more scientists studied Polaris, the more interesting it became. Because Polaris is not just a convenient marker in the sky, it is also a fascinating object in its own right. It is a giant star, far larger than our Sun. Its diameter is dozens of times greater, and its luminosity shines thousands of times brighter. If Polaris replaced the Sun in our solar system, its outer atmosphere would extend past the orbit of Mercury. Yet even that description only scratches the surface of what makes Polaris important. The star is also a variable star, meaning its brightness changes slightly over time as its outer layers expand and contract. These pulsations reveal information about the internal physics of the star itself. Astronomers learned that stars like Polaris belong to a category known as Cepheid variables. These stars follow a predictable relationship between how fast they pulse and how bright they truly are. That relationship turns Cepheid stars into one of the most powerful tools astronomers have for measuring distances across the universe. By observing how quickly a Cepheid brightens and dims, scientists can determine its intrinsic brightness. Comparing that true brightness with how bright it appears from Earth allows them to calculate its distance. In other words, stars like Polaris helped astronomers build the first reliable cosmic measuring sticks. But before we drift too far into stellar physics and cosmic distances, there is still something quietly fascinating about the simple view from Earth. Because even though the sky appears to spin around Polaris, the motion we observe is only the first layer of a much larger set of movements. Earth rotates. Earth orbits the Sun. The Sun orbits the centre of the Milky Way galaxy. And Polaris itself moves along its own path through space. All of those motions combine into an enormous cosmic dance that unfolds across millions and billions of years. Yet from our small vantage point on the surface of a spinning planet, the result appears deceptively simple. The stars circle overhead, and one of them barely moves. From that single visual clue, humans discovered the rotation of Earth, the geometry of the planet, and eventually the structure of the sky itself. So the next time you imagine the North Star, it helps to remember that its importance does not come from being the brightest star, or the largest, or the closest. Its importance comes from geometry, from the quiet alignment between a spinning planet and a distant star that happens to lie almost perfectly along the direction of Earth's axis. A small coincidence of cosmic angles turned Polaris into one of the most useful points in the sky. Take a moment and imagine yourself standing outside on a very clear night. There is no hurry, no bright city lights washing out the sky, just a wide, quiet darkness above you and thousands of stars scattered across it. At first glance, everything looks completely still. The stars seem fixed in place, as if they were tiny holes in a dark dome. Many people throughout history believed something very much like that. The sky looked solid, almost like a gigantic sphere with lights embedded in it. But if you remain there long enough, something curious begins to happen. Very slowly, almost imperceptibly at first, the sky begins to move. The stars do not stay where they were. Instead, they drift across the darkness in gentle arcs. A constellation that was just rising above the horizon gradually climbs higher. Another one that was overhead begins sliding toward the opposite side of the sky. After several hours, some stars disappear below the horizon entirely while new ones rise to replace them. This movement is not chaotic. It is smooth, predictable, and incredibly consistent. Night after night, the same patterns repeat. Stars rise, travel across the sky, and set again with remarkable regularity. For ancient observers who watched the sky carefully, this behaviour became one of the first clues that something very large and very steady was happening to the world itself. From our everyday perspective, the ground beneath our feet feels completely motionless. Trees do not slide sideways. Buildings do not lean or drift. The oceans do not slosh endlessly toward one side of the planet. Everything appears stable and fixed. Yet the sky suggests otherwise. The steady motion of the stars tells us something fundamental about the physics of our planet. Earth is rotating. This might sound obvious today because most of us learned it early in school, but for much of human history the idea was deeply counterintuitive. If the ground was spinning, people reasoned, surely we would feel it. Objects might fly off the surface or winds would rage constantly in one direction. Instead, the world felt calm and stable, while the heavens above seemed to do all the moving. For thousands of years, many cultures assumed the sky itself was rotating around Earth. It was a natural conclusion based on observation alone. Every night the stars seemed to circle overhead, always following the same paths. The explanation eventually became clear once scientists began carefully studying motion and inertia. Earth rotates once every 24 hours, completing a full turn around an imaginary line running through the planet from the North Pole to the South Pole. This line is called Earth's rotational axis. You can think of it as the same kind of axis that runs through a spinning top or a rotating wheel. Everything on Earth rotates together with the planet. The ground, the oceans, the atmosphere, the buildings, and our own bodies all move with the same motion. Because everything shares the same rotation, we do not notice it in our everyday experience. It is similar to sitting inside a smoothly moving train. When the train glides forward at a steady speed, you can stand, walk, or pour a drink without feeling the motion very strongly. Only when the train accelerates or slows down do you feel the change. Earth's rotation is steady and continuous, so our bodies simply move with it. The stars, however, do not rotate with Earth. They remain extremely far away in space, effectively fixed relative to us on the timescale of a single night. As our planet spins beneath them, our viewpoint slowly changes, and the stars appear to move across the sky. From our perspective, it looks as though the sky is rotating. But in reality, it is we who are turning. This simple shift in perspective reveals something fascinating about the geometry of the night sky. If Earth rotates around an axis, then every point on the planet traces a circular path around that axis once every day. At the equator, the circle is very large, because those locations are far from the axis. Near the poles, the circle becomes smaller and smaller, until at the exact north or south pole, the circle shrinks to a single point. Now imagine extending Earth's axis outward into space. If the axis continued past the North Pole into the sky, it would point toward a specific direction among the stars. That direction is known as the North Celestial Pole. Every star in the sky appears to move in circles centered on that point. When you observe the stars over many hours, their paths trace these circular arcs. Some stars rise and set because their circular paths dip below the horizon. Others, closer to the North Celestial Pole, never set at all. They simply rotate endlessly around the pole like slow-moving lights on a giant wheel. These stars are known as circumpolar stars because they circle the pole. And very near the centre of that motion sits Polaris. Because Polaris lies extremely close to the North Celestial Pole, its circular motion across the sky is very small. Instead of tracing a wide arc like most stars, it appears to remain almost perfectly fixed in place while the rest of the sky rotates around it. This visual effect has fascinated skywatchers for centuries. If you were to take a long exposure photograph of the night sky, leaving the camera open for several hours, the stars would appear as long curved streaks of light. Every streak would form part of a circle centered on Polaris. The entire sky would look like a spinning wheel of light with Polaris near its hub. The motion of those circles directly reveals Earth's rotation, but the story becomes even more interesting once we consider how fast the planet is actually spinning. Earth completes one full rotation every 24 hours, which means a point on the equator travels an enormous distance in that time. The circumference of Earth at the equator is roughly 40,000 kilometers. Divide that by 24 hours, and the surface of the planet there moves at about 1,600 kilometers per hour. That is faster than most commercial airplanes, yet we feel none of it because the motion is constant and shared by everything around us. As you move away from the equator toward the poles, the rotational speed decreases. Locations closer to the axis travel along smaller circles during each rotation. At the poles themselves, the speed becomes effectively zero, because those points lie directly on the axis of rotation. This variation in speed has interesting consequences for the sky. Near the equator, the stars rise almost vertically from the horizon, climb quickly overhead, and set again roughly 12 hours later. Observers there see the entire sky rotate dramatically each night. Farther north, the paths of the stars tilt. Some stars remain visible all night because their circular paths never dip below the horizon. Polaris gradually rises higher in the sky as you travel northward, reflecting your changing angle relative to Earth's axis. At the North Pole, the situation becomes especially striking. If you stood exactly at the North Pole and looked up at the sky, Polaris would appear almost directly overhead. The stars would rotate horizontally around the horizon rather than rising and setting. The entire sky would spin like a slowly turning ceiling. Each full circle would take 24 hours. This perspective reveals just how closely Polaris is connected to Earth's rotational axis. But the physics of Earth's rotation involves more than just geometry. The rotation itself has deep origins in the early history of the solar system. Around 4.5 billion years ago, Earth formed from a swirling cloud of gas, dust, and rocky debris orbiting the young sun. Within that rotating cloud, particles collided and merged, gradually building larger bodies called planetesimals. As these objects combined to form planets, they inherited the angular momentum of the rotating cloud. Angular momentum is a physical quantity that describes rotational motion. Once an object begins spinning, it tends to keep spinning unless something interferes with it. This principle comes from the law of conservation of angular momentum. It's the same reason a spinning ice skater rotates faster when pulling their arms inward. By changing their shape, they redistribute angular momentum, causing their rotation to speed up. When Earth formed, countless collisions between large bodies helped shape its final rotation rate and orientation. Some of those impacts were enormous. One particularly dramatic collision likely created the Moon, when a Mars-sized body struck the young Earth billions of years ago. The aftermath of that impact altered Earth's rotation and tilted its axis slightly relative to its orbit around the Sun. Today that tilt is about 23.5 degrees. The tilt of Earth's axis is responsible for the seasons, but it also plays an important role in how the sky appears to move. Because the axis is tilted relative to the Sun, the positions of the stars shift gradually throughout the year as Earth travels along its orbit. Different constellations become visible during different seasons, but the daily motion of the sky, the steady rotation of stars around Polaris, comes directly from Earth's spin. Another interesting detail emerges when we consider that Earth's rotation is not perfectly constant forever. The gravitational interaction between Earth and the Moon creates tidal forces that slowly transfer angular momentum away from Earth's rotation. As a result, Earth's spin is gradually slowing down. The change is extremely small. Over the course of a century, the length of a day increases by only a few milliseconds. But over millions of years, the effect becomes noticeable. Hundreds of millions of years ago, A day on Earth was significantly shorter than 24 hours. Geological evidence suggests that during the time of the dinosaurs, Earth may have rotated fast enough that a full day lasted around 23 hours. Going even farther back in time, early Earth may have completed a rotation in less than 10 hours. The planet has been gradually slowing ever since. Despite this slow change, Earth's rotation remains remarkably stable on human timescales. That stability allows the sky's daily motion to act like a cosmic clock. For ancient civilizations, the rising and setting of stars provided reliable markers of time and direction. Long before mechanical clocks or digital watches existed, people could measure hours by watching the sky. The rotation of Earth quietly organized human life. Farmers noticed which stars appeared before sunrise during certain seasons. Sailors navigated by tracking the paths of stars across the horizon. Travelers crossing deserts or oceans used the sky as a guide. At the center of this rotating sky stood Polaris. Because it marked the direction of Earth's axis, Polaris became a natural anchor point in the heavens. While the rest of the stars wheeled around it, Polaris remained almost fixed. Its stillness revealed the hidden motion of our planet. The simple observation that the sky rotates around a single point eventually helped scientists understand the true structure of Earth's motion. Instead of the universe spinning around us, our own world was quietly turning beneath the stars. That realization marked one of the most important shifts in the history of science. Yet even with modern knowledge, there is still something quietly captivating about stepping outside and watching the stars drift slowly across the sky. The motion is gentle enough that you can almost forget it is happening, yet powerful enough to reveal the physics of an entire rotating planet. Step outside again in your mind for a moment and look upward. The sky stretches above you like a vast dome, and scattered across that dome are countless points of light. Even if you know quite well that space is unimaginably large and that the stars are separated by distances measured in trillions of kilometers, the sky still feels strangely close. It feels almost like a surface, as though the stars are attached to some enormous curved shell surrounding Earth. That impression is not unusual. In fact, it is exactly how many ancient astronomers described the heavens. They imagined the stars fixed on a giant sphere that surrounded the planet. This sphere slowly rotated once every day, carrying the sun, the moon, and the stars across the sky. Today we know the universe is far more complex than that picture suggests. Stars are not attached to any kind of cosmic shell. They exist at enormous distances from us, scattered throughout the Milky Way galaxy and far beyond it. Yet astronomers still use the idea of that imaginary sphere because it turns out to be extremely useful for understanding how the sky appears to move. This concept is called the celestial sphere. The celestial sphere is not a physical object. It is a mental model, a way of organizing the sky so that we can describe where things appear to be. Imagine that Earth sits at the center of a vast transparent sphere. The inner surface of that sphere is marked with all the stars we see in the night sky. From this viewpoint, every star appears to lie somewhere on the surface of the sphere, even though in reality they are scattered through space at very different distances. Using this imaginary sphere allows astronomers to describe positions and motions in the sky without needing to know how far away each star is. It simplifies a very complicated universe into something geometrically manageable. Now here is where the idea becomes particularly helpful for understanding why the sky appears to turn. Earth rotates around its axis once every 24 hours. Because we are standing on the surface of the rotating planet, our viewpoint constantly changes. As the planet turns, different directions in space come into view. When we use the celestial sphere model, it looks as though the sphere itself is rotating around us. The stars appear to move across its surface. From our perspective on Earth, the celestial sphere seems to rotate from east to west. Stars rise above the eastern horizon, travel across the sky, and eventually set in the west. But this motion is only an illusion created by Earth's rotation. The stars themselves remain almost perfectly fixed relative to each other over the course of a single night. Their apparent motion happens because our planet is turning beneath them. To visualize this more clearly, imagine placing small stickers on the inside of a large transparent globe. Now sit at the center of the globe and slowly rotate your chair. These stickers appear to move around you, even though they are not actually moving at all. The same effect occurs with the celestial sphere. Earth's rotation causes the sky to appear to rotate. This rotating sphere has a special axis, just like Earth does. If you extend Earth's rotational axis outward into space, it intersects the celestial sphere at 2 points. These points are called the celestial poles. One lies in the northern sky, and the other lies in the southern sky. The northern one is known as the North Celestial Pole, and very close to that point sits Polaris. Because Polaris lies so near the North Celestial Pole, it appears almost motionless as the celestial sphere turns. Other stars trace circular paths around the pole, but Polaris sits close to the center of that motion. This makes it look as though the entire sky rotates around Polaris. The celestial sphere model helps explain exactly how those circular paths appear. Imagine again the sphere surrounding Earth. As Earth rotates, the entire sphere seems to spin in the opposite direction. Every star follows a circular path around the celestial poles. The size of that circle depends on how far the star is from the pole. Stars close to the pole trace very small circles. Stars farther away trace much larger ones. Stars near the celestial equator travel the largest circles of all, rising and setting dramatically across the horizon each night. The celestial equator is another useful concept in this model. It is simply the projection of Earth's equator onto the celestial sphere. Just as Earth has a geographic equator dividing the northern and southern hemispheres, the celestial sphere has an imaginary line that divides the northern sky from the southern sky. Stars located on the celestial equator rise exactly in the east and set exactly in the west. Their paths across the sky form perfect semicircles. Stars north of the celestial equator spend more time above the horizon for observers in the northern hemisphere. Some never set at all. These stars circle the north celestial pole continuously. They are known as circumpolar stars. Polaris belongs to this group for most observers north of the equator. Circumpolar stars move in complete circles around the celestial pole without ever dipping below the horizon. If you watch them for an entire night, you would see them trace graceful arcs that eventually close into full circles. Photographers sometimes capture this effect by leaving a camera shutter open for several hours. The result is a striking image of star trails, where the stars appear as curved lines of light sweeping across the sky. At the center of those circles lies Polaris. The celestial sphere model also explains why different parts of the sky become visible as you travel across Earth. Your position on the planet determines which part of the celestial sphere lies above your horizon. Imagine standing somewhere in the northern hemisphere. The north celestial pole will appear above the northern horizon. The farther north you travel, the higher the point climbs in the sky. At the North Pole itself, the North Celestial Pole sits directly overhead. The celestial equator, meanwhile, forms a circle around the horizon. Half the sky remains permanently visible, while the other half never rises above the horizon. If you move southward toward the equator, the celestial poles shift toward the horizon. At the equator, the North Celestial Pole sits exactly on the northern horizon, and the South Celestial Pole sits on the southern horizon. From that location, every star rises and sets. None remain permanently above the horizon. Travel even farther south into the southern hemisphere, and the North Celestial Pole disappears entirely below the horizon. Polaris becomes invisible from those locations. Instead, the southern sky revolves around the South Celestial Pole, where a different set of stars forms the center of rotation. All of these patterns become much easier to understand when we picture the sky as a rotating sphere surrounding Earth. Even though we know that the stars are actually scattered throughout space at enormous distances, the celestial sphere remains one of the most practical tools for describing the sky. It also helps us understand something subtle about Polaris itself. Polaris is often called the fixed star, but that description is only approximately correct. Because Polaris is not exactly aligned with the North Celestial Pole, it traces a tiny circular path around the pole each day. The circle is so small that most observers never notice it with the naked eye. Over the course of 24 hours, Polaris shifts slightly in position as Earth rotates, completing a small circle in the sky. Astronomers can measure this motion precisely with telescopes, revealing that Polaris lies less than 1 degree from the true North Celestial Pole. This small offset explains why Polaris appears nearly stationary, while the rest of the sky rotates dramatically around it. But even this apparent stability hides a deeper layer of motion. The celestial sphere itself slowly changes over long periods of time because Earth's axis does not point in exactly the same direction forever. A slow gravitational wobble causes the axis to trace a circle in space over thousands of years. As the axis shifts, the position of the celestial poles also shifts across the sky. That means the centre of the celestial sphere's rotation slowly moves from one star to another over very long timescales. Polaris happens to lie near the pole during the current era of human history. Thousands of years ago, a different star occupied that position. Thousands of years in the future, another star will take its place. The celestial sphere will still appear to rotate, but the central point of that rotation will drift gradually across the sky. Even so, the basic geometry remains the same. Earth rotates. Our viewpoint changes. The sky appears to turn. The celestial sphere gives us a simple way to visualize that motion and understand why stars follow the paths we see each night. And when you look up long enough to notice those slow arcs sweeping across the darkness, you're watching the evidence of a rotating planet beneath your feet, a motion that began billions of years ago and continues without pause today. The stars themselves are not spinning around us at all. Instead, we are quietly turning beneath them, carrying the entire sky across our field of view once every day. And near the centre of that vast turning sphere sits Polaris, marking the direction of Earth's axis and anchoring the geometry of the sky in a way that has guided observers for centuries. If you picture Earth from far out in space, floating quietly in the dark with sunlight touching one half of the planet and shadow covering the other, one detail becomes immediately important. Our planet is not just drifting through space, it is spinning. This rotation happens around an imaginary line that passes through Earth from top to bottom. That line runs between the North Pole and the South Pole. It is called Earth's rotational axis. Even though the axis is not something you can see or touch, it is one of the most important directions in the entire universe from our point of view. Nearly everything about the way the sky behaves depends on it. Every 24 hours, Earth turns once around this axis. Because of that motion, different parts of the planet move into sunlight and then back into darkness. That is the basic reason we experience day and night. But the axis does more than divide day from night. It also determines how the entire sky appears to move above us. Imagine holding a basketball and pushing a pencil straight through its centre from top to bottom. The pencil represents the axis. If you spin the ball around that pencil, every point on the surface moves in a circular path around the axis. Earth behaves in exactly the same way. Every location on the planet traces a circle around the axis once each day. The size of that circle depends on how far the location is from the axis. Places near the equator travel along large circles. Places near the poles travel along much smaller ones. At the poles themselves, the motion becomes almost perfectly centered around the axis. Now extend that imaginary axis outward into space. Instead of stopping at the surface of Earth, imagine the line continuing indefinitely in both directions. One end of the axis points into the northern sky, the other points into the southern sky. Where those extensions intersect the celestial sphere, they define the celestial poles. The North Celestial Pole lies very close to the position of Polaris. That single fact explains why Polaris appears almost perfectly still, while the rest of the sky turns around it. The star sits nearly in line with Earth's axis. Because Earth spins around that axis, the sky appears to rotate around the same direction. It is similar to watching the ceiling above a spinning carousel. If you look straight up at the centre of the rotation, that point seems to stay almost fixed while everything around it moves. Polaris plays that role in the sky. This alignment gives the star a special significance. It marks the direction of Earth's axis in space. Wherever you are in the northern hemisphere, if you look toward Polaris, you're looking almost exactly along the direction of that axis. That means you're also looking almost exactly toward the geographic North Pole. This is why Polaris became such a valuable navigational guide. The star effectively points north. Yet the importance of the axis goes deeper than navigation. The direction Earth's axis points determines how the sky is arranged around us. Imagine Earth did not have an axis pointing in a particular direction. Without rotation, there would be no daily motion of the sky at all. Stars would remain fixed in their positions relative to the horizon. The concept of rising and setting stars would disappear. Instead, the axis creates a structured pattern in the sky. All stars appear to move along circular paths centered on the celestial poles. Those circles form the basic geometry of the heavens. From this perspective, the axis acts like the central pivot of the entire sky. Everything revolves around it, but the axis also introduces another interesting detail about Earth. It is tilted. Earth's axis does not stand straight up relative to its orbit around the Sun. Instead, it leans slightly, tilted by about 23.5 degrees. That tilt plays a crucial role in the behaviour of sunlight throughout the year. As Earth orbits the Sun, the tilt causes different hemispheres to receive more or less sunlight at different times. This is what creates the seasons. When the northern hemisphere tilts toward the Sun, it receives more direct sunlight and experiences summer. At the same time, the southern hemisphere tilts away from the Sun and experiences winter. 6 months later, the situation reverses. Although this seasonal effect mostly influences climate and daylight length, it also changes how the sky appears over the course of a year. As Earth travels around the Sun, the nighttime side of the planet faces different directions in space. That means different constellations become visible during different seasons. During winter evenings in the northern hemisphere, Orion stands prominently in the sky. During summer evenings, the bright stars of Scorpius and Sagittarius dominate the view. Yet through all those seasonal changes, the direction of the axis remains almost fixed in space. That stability keeps the North Celestial Pole in nearly the same location among the stars. And because Polaris lies close to that direction, it remains the North Star night after night. If you observe Polaris carefully over a long period, however, you will notice that it is not perfectly fixed. The star traces a very small circle around the exact location of the North Celestial Pole. The circle is tiny, only about a degree wide, but it reveals that Polaris is not exactly aligned with Earth's axis. Even so, it is close enough that its motion is barely noticeable without careful measurement. But there is another subtle feature of Earth's axis that becomes important when we consider very long periods of time. The axis itself is not perfectly stable forever. It slowly changes direction. This motion is known as axial precession. The change is extremely gradual. It takes about 26,000 years for Earth's axis to complete one full wobble. To understand what precession means, think about a spinning top. When a top spins rapidly, it stands upright. But if you watch closely, the top's axis slowly traces a circle as it spins. The top does not fall over immediately. Instead, its axis wobbles gently. Earth behaves in a similar way, although the motion is much slower, and caused by gravitational forces from the Sun and Moon. Over thousands of years, the direction of Earth's axis slowly sweeps across the sky. As the axis moves, the North Celestial Pole also moves. That means the star closest to the pole changes over time. Polaris holds that position now, but it has not always been the North Star. Several thousand years ago, a different star was closer to the North Celestial Pole. Thousands of years in the future, another star will take Polaris's place. The sky's central pivot slowly shifts as Earth's axis traces its long circular motion. Despite this slow change, the axis still provides a stable direction for human timescales. For many generations, Polaris remains close enough to the pole that it serves as a reliable marker of north. That reliability is one of the reasons Polaris became such an important reference point for explorers and astronomers. But the axis also tells us something about the broader motion of our planet through space. Earth rotates around its axis. At the same time, it orbits the Sun once every year, and the Sun itself moves through the Milky Way galaxy along a vast orbit that takes hundreds of millions of years to complete. All of these motions happen simultaneously. From our position on Earth, however, the rotation around the axis dominates our daily experience. It shapes the rhythm of day and night and creates the turning sky we observe each evening. Every time the stars drift slowly from east to west across the sky, they are revealing the motion of the planet beneath us. Polaris marks the direction of that motion. The star quietly indicates where the axis points, providing a reference for the entire structure of the sky. And because that direction in space remains nearly constant over human lifetimes, it gives the sky a sense of order. Constellations rotate predictably around the pole. Circumpolar stars trace their endless circles. Navigators can determine direction simply by locating Polaris. All of this begins with the axis of Earth. One imaginary line passing through the planet determines how the sky appears to move, how seasons unfold, and why one particular star seems to stand almost perfectly still. If you step outside on a clear evening in the northern half of the world and give your eyes a few minutes to adjust to the darkness, the sky slowly begins to reveal more detail. At first, only a handful of bright stars appear, but soon dozens become visible, and then hundreds. Patterns start to emerge among them, shapes that people long ago connected into constellations. Some of those patterns drift steadily across the sky as the night passes. A constellation that rises in the northeast will climb higher hour by hour. Another one already overhead will gradually slide toward the western horizon. If you remain outside long enough, you begin to notice that every star follows a curved path. Yet one point of light behaves differently. Near the northern part of the sky sits a star that seems almost perfectly fixed. While everything else slowly sweeps around it, that star barely moves at all. It becomes a quiet anchor point in the heavens, the centre of a giant turning pattern. That star is Polaris. To understand why Polaris behaves this way, we need to look closely at the exact direction Earth's axis points in space. Earlier, we talked about how Earth rotates around an imaginary line that runs through the planet from the South Pole to the North Pole. If that line is extended far beyond Earth into space, it points toward a very specific direction among the stars. That direction is called the North Celestial Pole. The North Celestial Pole is not a physical object. It is simply the point in the sky that lies directly above Earth's North Pole. It marks the direction in which Earth's rotational axis is aimed. You can picture it as the point where the axis would intersect the celestial sphere if the sphere truly existed as a solid surface surrounding our planet. Every star in the sky appears to move in circles around this point because Earth itself is rotating. As our planet turns, our viewpoint shifts, and the stars seem to trace circular paths centered on the celestial pole. If there were a star located exactly at the North Celestial Pole, that star would appear completely motionless. It would not rise or set. It would not drift across the sky. It would simply remain fixed in place while the rest of the heavens turned around it. For observers in the northern hemisphere, such a star would mark true north perfectly. But nature rarely produces such perfect alignments. Polaris happens to lie extremely close to the North Celestial Pole, but not exactly on it. The difference is very small, less than a single degree of separation. Because of this slight offset, Polaris does move, but its motion is tiny. Over the course of 24 hours, the star traces a small circle around the true North Celestial Pole. The circle is so small that most people never notice it with the naked eye. Instead, Polaris appears almost stationary. Meanwhile, every other star describes a much larger circle around the same centre. The farther a star is from the pole, the wider its circular path becomes. This simple geometry explains the remarkable behaviour of the night sky. The sky appears to rotate around Polaris, not because Polaris is special in itself, but because it lies very close to the direction Earth's axis points toward. In reality, the centre of the rotation is the north celestial pole. Polaris just happens to sit nearby. This distinction might sound subtle, but it matters when astronomers measure positions in the sky with precision. Instruments can determine the exact location of the celestial pole and track how stars move relative to it. Polaris is offset slightly, so it slowly circles that point each day. Still, for practical purposes, Polaris serves as an excellent marker of the pole. Its position changes so little that it remains a reliable reference for navigation and orientation. If you want to see this relationship more clearly, there is a simple observation you can try. Find Polaris in the night sky and watch it carefully over several hours. Compare its position to nearby stars. You will notice that the surrounding stars gradually move along curved paths, slowly circling around Polaris. But if you track Polaris itself relative to the exact centre of those circles, you will find that it shifts slightly. That shift reveals the true position of the north celestial pole. Astronomers sometimes use long exposure photographs to illustrate this effect. When a camera shutter remains open for hours, the stars leave trails of light on the image. These trails form curved arcs that all share a common centre. That centre marks the north celestial pole. Polaris appears as a short arc near the middle of the pattern, rather than a single fixed point. The effect is subtle but unmistakable once you know what to look for. This geometry also explains why Polaris becomes higher in the sky as you travel northward on Earth. Because Polaris lies close to the celestial pole, its altitude above the horizon corresponds closely to your latitude on Earth. If you stand at 30 degrees north latitude, Polaris will appear roughly 30 degrees above the northern horizon. At 40 degrees north, it rises about 40 degrees above the horizon. At the North Pole itself, Polaris sits almost directly overhead. The star's altitude mirrors your position on the planet. This relationship occurs because the celestial pole itself reflects the orientation of Earth's axis. When you move north or south across the surface of the planet, your angle relative to that axis changes. Polaris moves accordingly. For navigators, this simple geometric rule became an invaluable tool. By measuring the angle between Polaris and the horizon, sailors could determine their latitude while travelling across open oceans. The instrument used for this measurement was often a sextant or an astrolabe. These devices allowed observers to calculate the angle between a star and the horizon with surprising accuracy. Once they knew the altitude of Polaris, they could estimate how far north or south they were on Earth. This technique guided ships across vast distances long before modern navigation systems existed. Polaris therefore became more than just a reference point in the sky. It became a practical tool for finding one's position on the planet. But the story does not end there. The North Celestial Pole itself is not permanently fixed among the stars. Over extremely long periods of time, the direction of Earth's axis slowly changes. This motion is called axial precession. Earlier we mentioned that Earth behaves somewhat like a spinning top. Just as the axis of a top slowly wobbles as it spins, Earth's axis traces a very slow circle in space. One complete cycle of this wobble takes about 26,000 years. As the axis moves, the position of the celestial poles also shifts across the sky. This means the star closest to the north celestial pole changes over time. Polaris happens to be near the pole during the current era of human history, but it has not always held that position. Around 5,000 years ago, a different star named Thuban, in the constellation Draco, was much closer to the celestial pole than Polaris is today. Ancient Egyptian astronomers likely used that star when aligning their monuments with the sky. Thousands of years in the future, another star will take Polaris's place as the nearest visible marker of the pole. The celestial pole will slowly drift away from Polaris and toward a new star. But because precession occurs so gradually, Polaris remains close to the pole for many centuries. During this period, it continues to serve as the most convenient guide to the direction of Earth's axis. This shifting alignment between Earth's axis and the stars reveals something fascinating about our place in the universe. The sky we see today is not exactly the same sky that ancient civilizations observed. The patterns of stars remain largely the same, but their positions relative to the celestial poles slowly evolve over time. What appears fixed to us is actually part of a much longer cosmic cycle. Polaris is currently the star nearest to the north celestial pole, but its role is temporary. Even so, it remains extraordinarily useful. When people look up at Polaris, they are essentially looking along the direction of Earth's axis itself. That direction connects our spinning planet to the wider universe. It defines north on Earth. It anchors the motion of the celestial sphere, and it provides a reference point that has guided travellers for centuries. People often describe Polaris as the star that does not move, but that description is not entirely accurate. Polaris does move. It simply moves far less than the other stars around it. The reason for that difference lies in a combination of geometry and rotational motion, and understanding it introduces one of the most useful ideas in observational astronomy: angular motion. When we watch objects in the sky, we're not measuring their motion across physical distances in space. The stars are far too distant for that to be noticeable on the timescale of a single night. Instead, we measure how their positions change relative to the sky itself. This type of motion is called angular motion. Angular motion describes how far an object moves across our field of view, measured as an angle rather than a distance. Astronomers usually measure angles in degrees. A full circle contains 360 degrees, and the sky above us can be imagined as a dome covering that circular range. If a star moves across a portion of the sky equal to 1 degree, it has shifted by 1 degree of angular motion. To get a sense of what a degree looks like in the sky, hold your arm straight out in front of you and raise your little finger. The width of that finger roughly covers 1 degree of sky. The moon and the sun each appear about half a degree wide. That means you could cover either one with the tip of your little finger held at arm's length. Now imagine watching a star move across the sky over the course of several hours. As Earth rotates, the star's position relative to the horizon gradually changes. That change is measured in angular motion. The important point is that all stars appear to move across the sky at nearly the same angular speed. Because Earth rotates once every 24 hours, the entire sky appears to rotate 360 degrees during that time. If you divide 360 degrees by 24 hours, you find that the sky appears to rotate about 15 degrees every hour. Every star participates in that motion. However, the paths those stars follow are not straight lines. They are circles centered on the celestial poles. This circular motion is the key to understanding Polaris. Stars far from the north celestial pole travel along very large circles. During a single hour, they move about 15 degrees along those circular paths, which makes their motion easy to notice. Stars closer to the celestial pole travel along much smaller circles. Even though they move at the same angular rate around the pole, the visible shift in their position becomes much smaller. Polaris lies extremely close to the center of this circular pattern. Because of that position, its circular path is tiny compared with the wide arcs traced by other stars. The situation can be compared to the motion of points on a spinning wheel. Imagine a bicycle wheel rotating. A point on the outer rim of the wheel travels a large distance during each rotation. Its motion is dramatic and easy to see. Now look at a point near the hub at the center of the wheel. That point still rotates, but the circle it traces is extremely small. Its motion is much harder to notice. The stars in the sky behave in a similar way. Those near the celestial pole correspond to points near the hub of the wheel. Polaris sits close to that hub. As Earth rotates, Polaris traces a small circular path around the north celestial pole. The circle is only about 1 degree wide. Over the course of 24 hours, Polaris slowly completes that circle. Because the circle is so small, the motion is subtle. To the naked eye, the star appears almost perfectly fixed. Meanwhile, stars farther from the pole travel much larger circles, making their motion far more noticeable. Another way to think about this is by imagining the sky as a giant rotating dome. At the top of that dome lies the north celestial pole. Polaris sits very near that point. When the dome rotates, areas near the top barely shift position relative to an observer. Areas farther down sweep across the sky in a wide arcs. Angular motion behaves exactly the same way. Everything rotates together, but the apparent movement depends on how far the object lies from the centre of rotation. The closer a star lies to the celestial pole, the smaller its visible motion becomes. Polaris happens to lie within roughly 3/4 of a degree of the true north celestial pole today. That proximity makes its motion extremely small compared with the rest of the sky. With careful observation over several hours, however, the movement can still be detected. Astronomers often demonstrate this by photographing the sky with long exposures. When a camera is left open for many minutes or hours, stars leave trails of light on the image as Earth rotates. These trails form arcs of circles centered on the celestial pole. Polaris appears as a short arc near the center of the pattern rather than a perfect dot. The length of that arc reveals how far Polaris lies from the exact pole. If Polaris were exactly aligned with the pole, it would appear as a single point with no visible trail. The existence of that small arc shows that Polaris is slightly offset. Even though its movement is tiny, it still participates in the same rotational motion as every other star. Understanding angular motion also explains why some stars never set below the horizon. Stars that lie close enough to the celestial pole trace circles that remain entirely above the horizon for observers in the northern hemisphere. These are the circumpolar stars. As Earth rotates, they move around the pole but never disappear below the horizon. Observers farther north see more circumpolar stars because the celestial pole appears higher in the sky. Polaris, sitting close to the pole, belongs to this group for most locations north of the equator. This is another reason it became such a reliable guide for navigation. Unlike many stars that rise and set, Polaris remains visible throughout the entire night. Its nearly constant position allowed travellers to determine direction regardless of the time. The concept of angular motion also reveals something interesting about how we measure positions in the sky. Astronomers divide the celestial sphere into coordinates similar to the latitude and longitude used on Earth. These coordinates are called declination and right ascension. Declination measures how far north or south a star lies relative to the celestial equator. Right ascension measures its position east or west along the sky. The north celestial pole lies at a declination of plus 90 degrees. Polaris has a declination slightly less than that value, because it sits a small distance away from the exact pole. That small difference explains its tiny circular motion. As Earth rotates, Polaris appears to move around the pole while maintaining nearly the same declination. For casual observers, the motion is almost invisible, which is why Polaris gained its reputation as a fixed star. Still, even Polaris is not completely stationary over long periods of time. Beyond the daily rotation of Earth, the orientation of Earth's axis slowly changes due to axial precession. This gradual wobble shifts the location of the celestial poles across the sky over thousands of years. Because of this slow motion, the distance between Polaris and the north celestial pole changes over time. Several centuries ago, Polaris was farther from the pole than it is today. Over the next century, it will move even closer before gradually drifting away again as precession continues. This slow shift means Polaris's tiny circular path will shrink slightly before expanding again in the distant future. Although the effect unfolds across generations, it reminds us that even the most stable reference points in the sky are part of larger motions. everything in the universe moves. The apparent stillness of Polaris is simply a result of perspective and geometry. From our vantage point on a rotating planet, the star lies almost exactly along the direction of Earth's axis. Because of that alignment, its angular motion across the sky remains extremely small. The rest of the heavens appear to sweep dramatically around it, creating the impression that Polaris anchors the entire sky. Yet the truth is more subtle. Polaris moves along a small circle around the celestial pole. Earth rotates beneath the stars, and the sky we see each night reflects the geometry of those motions combined. Once this idea of angular motion becomes clear, it also reveals something deeper about Polaris itself. The star is not only positioned near the celestial pole, it is also a physical object with its own motion through space, its own structure, and its own history. Long before satellites, radio navigation, or digital maps existed, travellers had to determine their position on Earth using far simpler tools. Oceans stretched for thousands of kilometres without landmarks. Deserts and plains offered few reliable reference points. Anyone attempting a long journey across such landscapes needed a dependable way to figure out where they were. The sky provided that solution. Among the countless stars above, Polaris offered something remarkably useful. It did not just indicate the direction of north, it also revealed how far north or south a person was on the planet. That ability comes directly from the geometry of Earth and the position of Polaris near the north celestial pole. Understanding this relationship begins with a concept called latitude. Latitude measures how far north or south a location lies relative to the equator. The equator itself sits at 0 degrees latitude. The North Pole lies at 90 degrees north latitude, while the South Pole lies at 90 degrees south latitude. These measurements are based on angles. Imagine standing at the centre of Earth and drawing lines outward to different points on the surface. The angle between those lines and the equatorial plane defines latitude. A location halfway between the equator and the North Pole sits at 45 degrees north latitude. Now consider what happens when you extend Earth's axis into space. Earlier we discussed how the planet rotates around an imaginary line connecting the North Pole and the South Pole. When that axis is extended outward beyond Earth, it points toward a specific direction among the stars. That direction marks the North Celestial Pole. Polaris happens to lie extremely close to that point. This alignment creates a simple but powerful geometric relationship between Polaris and any observer standing on Earth. Wherever you stand in the northern hemisphere, the angle between Polaris and the horizon corresponds closely to your latitude. If you are located at 30 degrees north latitude, Polaris appears about 30 degrees above the northern horizon. If you travel farther north to 50 degrees latitude, Polaris rises higher in the sky and appears about 50 degrees above the horizon. At the North Pole, Polaris sits almost directly overhead, roughly 90 degrees above the horizon. The reason for this pattern becomes clear when we imagine Earth as a sphere. Picture the planet from space. The rotational axis passes through the centre and points toward the North Celestial Pole. Polaris lies near that direction. Now imagine a person standing somewhere on the surface of Earth. Their horizon forms a flat plane that touches the sphere at their location. The angle between that horizon and the direction toward the North Celestial Pole determines how high Polaris appears in their sky. As the observer moves northward across the planet, their orientation relative to Earth's axis changes. Their horizon tilts relative to the direction of the axis. Because Polaris lies along that direction, the star rises higher above the horizon. This effect can be visualized with a simple model. Imagine placing a small figure on the surface of a globe. Draw a line from that figure's position toward the center of the globe. That line represents the direction of gravity for the observer. Their horizon forms a plane perpendicular to that line. Now extend the globe's rotational axis outward into space. The angle between the observer's horizon and the axis corresponds directly to the observer's latitude. Since Polaris lies near the axis, its height above the horizon matches that same angle. the geometry works out perfectly. This relationship allowed early navigators to determine their position with surprising accuracy using only simple instruments. By measuring the altitude of Polaris above the horizon, they could estimate their latitude on Earth. The measurement itself was usually made with tools such as an astrolabe, a quadrant, or later a sextant. These devices measured angles between celestial objects and the horizon. A sailor would sight Polaris through the instrument and read the angle indicated by the scale. That angle gave an immediate estimate of latitude. If Polaris stood 40 degrees above the horizon, the ship was near 40 degrees north latitude. This method became one of the foundations of navigation for centuries. It worked because Polaris remained visible throughout the night for most northern observers, and its position relative to the celestial pole changed very little. However, the method required careful observation. The horizon had to be clearly visible, which was sometimes difficult on rough seas. The altitude of Polaris also changes slightly throughout the night, because the star traces a small circle around the north celestial pole. Navigators often accounted for this by taking multiple measurements and averaging them. Even with these complications, the technique was remarkably effective. For travellers crossing the Atlantic Ocean or exploring distant coasts, Polaris served as a reliable reference for determining how far north or south they had travelled. Another interesting consequence of this geometry appears when someone travels southward toward the equator. As the observer moves south, Polaris gradually sinks lower in the northern sky. At 20 degrees north latitude, Polaris stands 20 degrees above the horizon. At 10 degrees north, it stands only 10 degrees high. Eventually, at the equator, Polaris sits almost exactly on the northern horizon. Beyond that point, the star disappears entirely. Observers in the southern hemisphere cannot see Polaris at all, because the curvature of Earth blocks the view. From those latitudes, the north celestial pole lies below the horizon. The southern sky instead rotates around the south celestial pole, which lies in a region of sky without a bright star marking its location. This difference between hemispheres illustrates how strongly the appearance of the sky depends on the observer's position on Earth. Every location on the planet has its own horizon and its own perspective on the celestial sphere. Yet the relationship between latitude and the altitude of Polaris remains consistent for all observers in the northern hemisphere. Because of this simple geometric rule, Polaris became an essential tool not only for sailors, but also for explorers, cartographers, and astronomers. During the Age of Exploration, European navigators relied heavily on Polaris to determine their latitude while crossing unfamiliar oceans. Ships travelling west across the Atlantic maintained their course by keeping Polaris at a constant altitude. If the star rose higher than expected, the ship had drifted north. If it sank lower, the vessel had moved too far south. Correcting the course restored the desired latitude. This technique allowed sailors to follow what were known as latitude sailing routes. By maintaining a constant latitude, ships could travel long distances across open water while staying aligned with their intended destination. Of course, determining longitude, the east-west position on Earth, was much more difficult and required precise timekeeping. That problem would not be solved reliably until the invention of accurate marine chronometers in the 18th century. But latitude could be measured simply by observing Polaris. The geometry of the sky made it possible. Astronomers later refined these measurements even further. By accounting for small corrections caused by atmospheric refraction and the slight offset between Polaris and the true celestial pole, they could determine latitude with impressive precision. Modern instruments and satellite systems have largely replaced these techniques today, but the underlying geometry remains exactly the same. Polaris still reveals the orientation of Earth's axis in space, and wherever you stand in the northern hemisphere, the height of that star above the horizon still corresponds closely to your latitude. Looking up at Polaris therefore provides more information than many people realize. The star marks the direction of north. It marks the location of the celestial pole, and through a simple angular measurement, It reveals your position on Earth's curved surface. All of this emerges from the geometry of a rotating sphere. Earth spins around its axis. The axis points toward the north celestial pole. Polaris lies near that direction, and the angle between the pole and your horizon tells you exactly how far north you are. This elegant relationship between sky and planet helped humans navigate the world long before modern technology existed. Not everything about Earth's orientation in space is perfectly fixed. The planet rotates steadily, completing one turn every 24 hours, and the axis of that rotation points toward a particular region of the sky. For our time in history, that direction lies very close to Polaris. The entire geometry of the northern sky seems organised around that alignment. However, the direction of Earth's axis is not permanently locked in place. Over very long stretches of time, the axis slowly changes orientation. The change is extremely gradual, far too slow to notice during a single lifetime, yet measurable across centuries and unmistakable across millennia. Astronomers call this motion axial precession. The word precession describes a slow wobble in the orientation of a rotating object. A simple spinning top provides a good comparison. When a top spins rapidly, its axis stands nearly upright, but if you watch carefully, you will notice that the axis does not remain perfectly still. It slowly traces a circle in space while the top continues to spin. Earth behaves in a similar way. Although the planet rotates steadily around its axis, that axis itself slowly sweeps out a circular path in space. The motion is extremely slow. Completing one full circle takes about 26,000 years. Because of this wobble, the direction in which the axis points gradually shifts relative to the stars. To understand why this happens, it helps to think about the shape of Earth. Our planet is not a perfect sphere. Instead, it bulges slightly around the equator due to its rotation. The centrifugal effect of spinning causes material near the equator to push outward, making the equatorial diameter slightly larger than the distance between the poles. This bulge may seem small, but it has important consequences. The Sun and the Moon both exert gravitational forces on Earth. Their gravity pulls on the equatorial bulge unevenly, because the bulge is tilted relative to the plane of Earth's orbit around the Sun. Those gravitational pulls act like tiny torques on the spinning planet. A torque is a force that changes the direction of rotation of an object. In the case of Earth, the gravitational torque from the Sun and Moon does not stop the planet from spinning. Instead, it gradually shifts the direction of the axis. This is exactly the same type of effect seen with a spinning top. Gravity pulls downward on the top's mass, creating a torque that causes the axis to wobble. The top continues spinning, but the direction of its axis slowly moves in a circle. For Earth, the process happens far more slowly because of the enormous mass involved and the relatively weak torques acting on the planet. Still, the result is a continuous slow drift of the axis across the sky. If you could watch Earth's axis from far away in space over thousands of years, you would see it tracing a circular path roughly 23 degrees wide. The tilt of Earth's axis relative to its orbit remains about the same, but the direction it points gradually rotates. This movement causes the position of the celestial poles to shift among the stars. At the moment, the north celestial pole lies very close to Polaris, which is why Polaris appears to mark the centre of the rotating sky. But thousands of years ago, the celestial pole pointed toward a different star. One of those earlier pole stars was Thuban, located in the constellation Draco. Around 4,000 to 5,000 years ago, during the era when the ancient Egyptians built many of their pyramids, Thuban lay very close to the north celestial pole. For observers of that time, Thuban would have served as the North Star rather than Polaris. As the centuries passed, the celestial pole slowly drifted away from Thuban and moved through different regions of the sky. Eventually it approached the current position near Polaris. Even today, Polaris is not exactly at the pole. Because precession continues, the pole is still moving slightly closer to Polaris. Around the year 2100, the two will reach their closest alignment. After that point, the pole will begin drifting away again. Over the next several thousand years, another star will gradually take Polaris's place as the nearest bright star to the north celestial pole. One future candidate is the star Gamma Cephei, which will lie close to the pole several thousand years from now. Farther in the future, the bright star Vega will become a prominent pole star. This slow cycle means the identity of the North Star changes throughout history. Each star that lies near the path of the celestial pole takes a turn, serving as the centre of the sky's rotation. The stars themselves do not move into those positions because of precession. Instead, Earth's axis changes direction, shifting the location of the pole across the sky. From our perspective on the surface of Earth, the result is a gradual migration of the pole among different stars. Axial precession also produces another noticeable effect in astronomy. The positions of the equinoxes slowly shift along Earth's orbit around the Sun. An equinox occurs when the Sun crosses the celestial equator, producing equal lengths of day and night across the planet. Because the orientation of Earth's axis changes over time, the location of these crossing points moves gradually relative to the background stars. This phenomenon is called the precession of the equinoxes. Ancient astronomers discovered this effect by comparing the positions of stars relative to the Sun during equinoxes over long periods of time. One of the earliest known descriptions of precession comes from the Greek astronomer Hipparchus in the 2nd century BCE. By comparing his observations with older records, he realized that the positions of certain stars relative to the equinoxes had shifted slightly. The shift was small but measurable. From that evidence, Hipparchus concluded that the orientation of Earth's axis must be slowly changing. Modern measurements confirm his conclusion with remarkable accuracy. The axis completes its full precession cycle in roughly 26,000 years. This means the celestial pole moves about 1 degree across the sky every 72 years. Although that motion is too slow to notice during everyday observation, it becomes clear when comparing astronomical measurements separated by centuries. Axial precession therefore reminds us that even the most stable features of the sky are part of larger cosmic motions. Polaris appears steady because our timescales are short compared with the length of the precession cycle. For thousands of years, Polaris remains close enough to the celestial pole to function as the North Star. Yet on the scale of tens of thousands of years, its role is temporary. Eventually the axis will drift far enough that Polaris will no longer occupy that special position. Another star will become the reference point around which the northern sky appears to rotate. This slow wobble of Earth also illustrates how gravitational interactions shape the behaviour of celestial bodies. The Sun and Moon exert forces on Earth that subtly influence its rotation. Over enormous timescales, those forces reshape the orientation of the planet itself. Even though the changes unfold slowly, they reveal that Earth's motion is part of a complex gravitational system involving multiple bodies. The sky we see today reflects the current orientation of that system. Polaris sits near the direction of Earth's axis, marking the location of the North Celestial Pole for our era. But the pole is quietly migrating across the sky as precession continues. Many centuries from now, observers will notice that Polaris has begun to drift farther from the pole. Future generations will identify a different star as the centre of the sky's rotation. Still, the geometry of the celestial sphere remains the same. Earth continues spinning, the sky continues appearing to rotate, and the direction of the axis continues guiding the motion of the stars across the night. For many people, Polaris carries an almost permanent reputation. It is often described as the North Star, the fixed point of the heavens, the star that has always guided travellers northward. The description sounds timeless, as if Polaris has occupied that position since the beginning of human history and will continue doing so indefinitely. Yet the reality is quite different. Polaris is only the North Star for now. That phrase may sound surprising at first. After all, Polaris appears to sit at the centre of the turning sky. Night after night it barely moves while the rest of the stars circle around it. For anyone observing the heavens during a single lifetime, the star seems completely stable. but the alignment that places Polaris near the north celestial pole is temporary. The slow wobble of Earth's axis, known as axial precession, gradually shifts the direction of the pole across the sky. Over thousands of years, the pole drifts among the stars, and the identity of the North Star changes along with it. To understand why this happens, it helps to picture the motion of Earth's axis in space. Earlier we compared the planet to a spinning top. When a top rotates, its axis does not remain perfectly upright. Instead, it slowly traces a circular path, wobbling gently as it spins. Earth behaves in much the same way. Although the planet rotates steadily once every day, the axis of that rotation gradually sweeps out a circle in the sky. Completing one full circle takes about 26,000 years. During that time, the North Celestial Pole moves across different constellations. As the pole moves, different stars come closer to that central position. Whichever star happens to lie nearest the pole at a given time becomes the North Star. This means the role of Polaris is simply one chapter in a long astronomical cycle. Thousands of years ago, Polaris was not the North Star at all. If we travel back about 5,000 years, to the era when early civilizations were developing agriculture and building some of the world's earliest monumental structures, the North Celestial Pole lay in a different region of the sky. At that time, the star closest to the pole was Thuban, located in the constellation Draco. Thuban is not nearly as bright as Polaris, but its position near the celestial pole made it the best guide for ancient skywatchers living during that period. Historical evidence suggests that some Egyptian pyramids were aligned with remarkable precision, using stars near the pole, including Thuban. To those observers, Thuban would have appeared to occupy the same special role that Polaris holds today. Over the centuries that followed, however, the slow motion of axial precession gradually shifted the pole away from Thuban. The star drifted farther from the centre of the sky's rotation. Eventually, the celestial pole moved into a region of the sky without any bright star nearby. For a long time, no particularly prominent star marked the pole clearly. Then the pole continued its slow journey. Around the past millennium, Polaris began moving closer to the pole. Its position improved steadily as precession carried the pole nearer to the star. Today, Polaris lies less than a degree away from the North Celestial Pole. That proximity makes it the best visible marker of the pole during our current era. But the motion has not stopped. Precession continues to move the pole across the sky even now. Over the next century, the pole will approach Polaris slightly more closely, before beginning to drift away again. After that, Polaris will slowly lose its privileged position. The pole will continue its long journey toward other stars. Several thousand years in the future, the star gamma Cepheid will become a closer marker of the pole than Polaris. Later still, the bright star Vega will move near the celestial pole. Vega is one of the brightest stars in the night sky, far brighter than Polaris. When Vega eventually takes its turn as the North Star roughly 12,000 years from now, the northern sky will look quite different. Observers living during that era will see Vega near the centre of the rotating sky, while Polaris will lie far from the pole. The cycle does not end there. After Vega's era passes, the celestial pole will continue drifting across the sky, eventually returning near Polaris again many thousands of years later as the full precession cycle completes. This repeating pattern means the identity of the North Star changes gradually throughout history. Each star's turn lasts several centuries or millennia, depending on how closely it lies to the path traced by the celestial pole. Polaris happens to occupy the most convenient position during the current part of the cycle. That timing is fortunate for modern observers because Polaris is relatively bright and easy to locate. Some earlier pole stars were much dimmer, making them less useful for navigation. Even so, Polaris is not perfectly positioned. Because the star lies slightly offset from the true North Celestial Pole, it traces a small circle around the pole each day as Earth rotates. The circle is tiny, but it reveals that Polaris is not exactly aligned with the axis. The true pole lies slightly away from the star. This small difference reminds us that the North Star is always an approximation rather than a perfect marker. Navigators and astronomers account for this offset when making precise measurements. The temporary nature of Polaris's role illustrates an important lesson about the sky. Although the stars seem fixed in their patterns, the structure of the heavens slowly evolves over long periods of time. The geometry of the celestial sphere changes as Earth's axis shifts direction. Constellations remain recognizable for thousands of years, but their orientation relative to the poles gradually alters. This slow transformation means that the night sky seen by ancient civilizations was not identical to the sky we observe today. Polaris was not the guiding star for early Egyptian astronomers. It will not remain the guiding star for distant future generations. The role of the North Star belongs to whichever star happens to lie closest to the celestial pole at a given moment in the long cycle of precession. From a human perspective, however, that cycle unfolds so slowly that Polaris appears permanent. A person could spend their entire life observing the sky and never notice any significant change in its position relative to the pole. For most practical purposes, Polaris functions as a fixed point. Yet astronomy reminds us that even this apparent stability is part of a larger cosmic motion. Earth's axis continues to wobble gently under the influence of gravitational forces from the Sun and the Moon. Over tens of thousands of years, that wobble gradually shifts the direction in which the axis points. As the direction changes, the center of the sky's rotation migrates from one star to another. Polaris simply occupies that position during the present stage of the cycle. Understanding this process helps explain why the concept of the North Star should be viewed as temporary rather than permanent. There is always a star closest to the celestial pole, but which star holds that title depends on when in history you happen to look. Today that star is Polaris. Thousands of years ago it was Thuban. Thousands of years from now it will be Vega. And as the cycle continues, other stars will briefly take the role before the pole eventually returns near Polaris once again. The quiet wobble of Earth ensures that the sky never stays exactly the same. Yet despite that slow change, Polaris still serves as an excellent guide for our time. Its position near the pole remains close enough that it marks north reliably for observers throughout the northern hemisphere. That usefulness explains why Polaris gained such a strong reputation as the guiding star of the north. But Polaris is more than just a convenient reference point. Polaris is not the brightest star in the sky. It does not dominate the heavens the way Sirius does in winter, or the way Vega shines during summer evenings. To the casual observer, it appears as a steady point of light, useful mainly because it marks the direction of north. Yet when astronomers began studying Polaris more closely, they discovered that the star itself is far more impressive than it appears from Earth. The first surprising detail involves distance. When you look at Polaris, the light reaching your eyes has travelled an extraordinary journey through space. The star lies roughly 430 light-years away from Earth. A light-year is the distance light travels in a single year, moving at about 300,000 kilometers per second. Over the course of a year, that speed carries light nearly 10 trillion kilometers. Multiply that enormous distance by 430, and the scale becomes difficult to imagine. The light leaving Polaris tonight will not reach Earth until sometime in the 25th century. At the same time, the light we currently see from Polaris began its journey in the early 17th century, during a period when telescopes were only just beginning to transform astronomy. This enormous distance explains why Polaris appears relatively faint compared with some other stars in the sky. Even though it shines with tremendous energy, much of that light spreads out across space before reaching our planet. Understanding the distance to Polaris was not easy. Early astronomers could estimate how bright the star appeared from Earth, but determining how far away it actually was required careful measurement of stellar parallax. Parallax is the slight shift in the apparent position of a nearby star when viewed from different points in Earth's orbit around the Sun. As Earth travels from one side of its orbit to the other over 6 months, nearby stars appear to shift slightly relative to more distant background stars. By measuring this tiny shift, astronomers can calculate how far away the star must be. For Polaris, the shift is extremely small, reflecting the star's great distance. Modern measurements using space telescopes and advanced detectors have refined the distance estimate to a high degree of accuracy. Once the distance is known, astronomers can determine something even more important about a star: its true luminosity. Luminosity describes the total amount of energy a star radiates into space. A star that appears bright in our sky might actually be relatively faint but close to Earth. Another star that appears dim might in reality be extremely powerful but located very far away. By combining the apparent brightness of Polaris with its measured distance, scientists can calculate how much energy the star truly emits. The result reveals that Polaris is vastly more luminous than our Sun. In fact, the North Star shines with roughly 2,000 times the luminosity of the Sun. If Polaris were placed at the centre of our solar system in place of the Sun, the amount of light and energy reaching Earth would increase dramatically. The temperature of the planet would rise enormously, and the entire solar system would be illuminated far more brightly than it is today. The reason Polaris produces so much energy lies in its size. Our Sun is a medium-sized star classified as a yellow dwarf. Polaris, by contrast, is a yellow supergiant. A supergiant star represents a later stage in stellar evolution. After spending millions or billions of years converting hydrogen into helium in their cores, many stars eventually exhaust their central hydrogen supply. When that happens, the internal structure of the star changes. The core begins to contract under gravity, heating up in the process. Meanwhile, the outer layers expand outward, increasing the star's radius dramatically. Polaris has reached this expanded stage. Its radius is dozens of times larger than that of the Sun. If Polaris replaced the Sun in our solar system, its outer atmosphere would stretch far outward, possibly reaching beyond the orbit of Mercury. Despite this enormous size, the star's surface temperature remains relatively moderate compared with many other stars. Polaris has a surface temperature of about 6,000 Kelvin, only slightly hotter than the Sun. Because of this temperature, Polaris emits light that appears white to the eye, but is often classified as yellow-white when astronomers analyse its spectrum. This colour corresponds to Polaris's stellar classification. Astronomers categorise stars using a system known as spectral classification. The system organises stars according to their surface temperature and spectral characteristics, assigning them letters such as O, B, A, F, G, K, and M. Each class represents a range of temperatures and colours. Hot blue stars belong to class O or B. Cooler red stars belong to class M. The Sun sits roughly in the middle as a G-type star. Polaris falls into the category of an F-type supergiant. F-type stars are somewhat hotter and more luminous than the Sun. When such stars evolve into supergiants, their brightness increases dramatically as their outer layers expand. This classification helps astronomers understand the physical processes occurring inside Polaris. The star's large size and high luminosity indicate that it has already progressed far beyond the main sequence stage of stellar evolution. It has exhausted the hydrogen fuel in its core and entered a new phase in which the internal structure becomes more complex. Inside Polaris, nuclear reactions continue to generate enormous amounts of energy. These reactions occur in layers surrounding the core, where hydrogen and helium fusion processes release energy that flows outward through the star. That energy eventually escapes into space as light and heat. Although Polaris appears calm and steady to the naked eye, the star's interior is a dynamic environment shaped by intense gravitational forces and nuclear reactions. Another interesting detail emerges when astronomers examine Polaris using telescopes capable of resolving fine structure. Polaris is not a single isolated star. It is part of a small multiple star system. The main star, often referred to as Polaris A, has at least 2 known companion stars bound to it by gravity. These companions orbit the primary star at different distances, forming a gravitationally connected system. The closest companion, Polaris AB, is a much smaller star orbiting relatively near the primary supergiant. Detecting this companion required powerful telescopes because the bright light from Polaris A overwhelms the faint glow of the smaller star. A second companion, Polaris B, lies farther away but is still gravitationally associated with the system. This arrangement makes Polaris a triple star system rather than a solitary star. Binary and multiple star systems are actually quite common in the universe. Many stars form in pairs or groups due to the way gas clouds collapse during star formation. The presence of companions around Polaris provides astronomers with additional opportunities to study the system. By observing the orbital motion of the stars, scientists can estimate their masses and better understand their physical properties. Mass is one of the most important characteristics of a star because it determines how the star evolves over time. Polaris has a mass several times greater than the Sun's mass, which explains why it has evolved into a supergiant more quickly than the Sun will. Massive stars consume their nuclear fuel at a faster rate, leading them through the stages of stellar evolution more rapidly. The Sun, by comparison, still has billions of years remaining before it reaches a similar phase. Observations of Polaris therefore provide insight into what happens to stars once they leave the stable phase of their lives. Despite its size and power, Polaris remains visually modest in the sky. Its brightness ranks around 50th among the stars visible to the naked eye. Many people are surprised to learn that the North Star is not especially bright compared with others. The reason it became famous has nothing to do with its luminosity. Its importance comes entirely from its location. Because Polaris lies near the North Celestial Pole, it appears nearly stationary while the rest of the sky rotates around it. That geometric alignment transformed an otherwise ordinary star into one of the most useful guides in the heavens. Yet the physical nature of Polaris reveals that the star is far from ordinary when viewed from an astrophysical perspective. It is a distant supergiant, radiating thousands of times more energy than the Sun and surrounded by companion stars. Not all stars remain the same throughout their lives. What we see as a stable point of light in the night sky is actually the visible stage of a long and complicated physical process, unfolding deep inside a sphere of hot gas. Every star begins its life by forming from a cloud of interstellar material, then evolves slowly as nuclear reactions transform the elements within its core. Polaris, despite its calm appearance, has already progressed far beyond the early stages of that journey. At the moment, Polaris belongs to a class of stars known as yellow supergiants. The name may sound simple, but it represents a very specific phase in stellar evolution. Reaching that stage requires millions of years of internal changes driven by gravity, pressure, and nuclear fusion. Understanding what is happening inside Polaris begins with the most fundamental force shaping every star: gravity. When a star forms, it begins as a collapsing cloud of gas and dust. Gravity pulls that material inward, causing the cloud to shrink and grow denser. As the gas falls toward the center, it heats up. Eventually, the pressure and temperature at the core become high enough to ignite nuclear fusion. Fusion is the process that powers stars. Inside a stellar core, hydrogen atoms collide under extreme pressure and temperature. These collisions allow hydrogen nuclei to combine, forming helium. During that process, a small portion of mass is converted into energy. According to Einstein's equation E equals mc square, that released energy travels outward through the star and eventually escapes as light and heat. For much of a star's lifetime, this process continues steadily. Gravity pulls inward while the energy from fusion pushes outward. The two forces balance each other, creating a stable structure. This balanced state is known as hydrostatic equilibrium. Our Sun is currently in this stable phase, which astronomers call the main sequence. During this period, a star spends most of its life converting hydrogen into helium in its core. Polaris, however, has already moved beyond that stage. The star began its life with a mass several times greater than the Sun's mass. Because massive stars burn their fuel more quickly, they evolve faster. Polaris exhausted the hydrogen supply in its central core much sooner than the Sun will. Once that fuel ran out, the internal balance of forces began to change. Without hydrogen fusion at the centre, the outward pressure supporting the core weakened. Gravity then caused the core to contract. As the core shrank, its temperature rose dramatically. The increase in temperature triggered new nuclear reactions in shells surrounding the core, where hydrogen continued to fuse into helium. Meanwhile, the contracting core heated enough to ignite helium fusion. Helium atoms began combining to form heavier elements such as carbon and oxygen. These processes released enormous amounts of energy. As energy flowed outward from the interior, the outer layers of Polaris expanded. The star's radius increased dramatically, transforming it into a supergiant. This expansion is why Polaris has grown so much larger than the Sun. Although its mass is only a few times greater than the Sun's, its radius has expanded to tens of times larger. If Polaris were placed at the centre of our solar system, its outer atmosphere would stretch far beyond the orbit of Mercury. Despite this large size, the surface temperature of Polaris remains only slightly hotter than that of the Sun. The star's temperature is roughly 6,000 Kelvin, which places it in the yellow-white portion of the stellar colour spectrum. This combination of large radius and moderate surface temperature gives Polaris its classification as a yellow supergiant. Inside such a star, the structure is layered. At the centre lies the dense core where helium fusion takes place. Surrounding the core are shells of gas where hydrogen continues to fuse into helium. Above those shells lie vast regions of hot plasma, where energy travels outward toward the surface. Energy moves through a star by two main processes. The first is radiation. In the radiative zones of a star, energy travels outward as photons. These photons interact constantly with particles of hot gas, scattering and being absorbed before continuing their journey outward. Even though light moves extremely fast, the repeated interactions slow its progress. A photon produced in the core of a star may take thousands or even millions of years to reach the surface. The second process is convection. In convective regions, hot gas rises toward the surface, while cooler gas sinks back toward the interior. This motion creates enormous circulating currents, somewhat similar to the movement of boiling water in a pot. In supergiant stars like Polaris, convection can dominate the outer layers. Large cells of rising and falling gas transport energy through the star's atmosphere. These internal motions play an important role in the behaviour of Polaris. The star does not remain perfectly stable in size or brightness. Instead, its outer layers expand and contract slightly over time. This pulsation occurs because of complex interactions between pressure, temperature, and gravity inside the star. During certain phases of its cycle, the outer layers expand outward. As they expand, the star's surface cools slightly and its brightness changes. Later, the layers contract again, heating up and altering the star's luminosity. The cycle repeats with remarkable regularity. Polaris belongs to a group of stars known as Cepheid variables. These stars pulsate in a predictable way, causing their brightness to vary over time. The pulsations of Cepheid stars are not random fluctuations. They arise from physical processes occurring in specific layers of the star's atmosphere. One key mechanism involves the ionization of helium. At certain temperatures, helium atoms lose electrons and become ionized. This ionized gas traps radiation more effectively than neutral gas, increasing pressure inside the layer. As the pressure builds, the outer layers of the star expand outward. When the gas cools again, helium recombines with electrons, allowing energy to escape more easily. The pressure drops, and gravity pulls the layers back inward. This repeating cycle produces the rhythmic pulsation observed in Cepheid stars. In the case of Polaris, the brightness changes are relatively subtle compared with many other Cepheid variables. The star's light fluctuates slightly over a period of a few days as its outer layers move in and out. Even though the changes are small, they provide valuable information about the internal structure of the star. Astronomers can measure the pulsation period of Polaris and relate it to the star's intrinsic luminosity. This relationship between pulsation period and luminosity is one of the most important tools in modern astronomy. Cepheid variables serve as cosmic measuring markers because their brightness variations reveal how luminous they truly are. By comparing the true luminosity with how bright the star appears from Earth, astronomers can determine its distance. This method has been used to measure distances to other galaxies, helping scientists map the structure of the universe. Polaris itself is one of the closest Cepheid variable stars to Earth, which makes it especially useful for calibrating these measurements. Studying Polaris also reveals how stars evolve as they pass through the supergiant phase. Eventually, as nuclear reactions continue in the core, the structure of the star will change again. Over extremely long timescales, Polaris will continue fusing heavier elements and shedding material into space. The outer layers of supergiant stars are often unstable. Strong stellar winds can carry gas away from the star, enriching the surrounding interstellar medium with heavier elements created through nuclear fusion. These elements later become part of new generations of stars and planets. Although Polaris currently appears calm and steady, the processes occurring inside it are far from quiet. Gravity compresses the core. Fusion reactions generate immense energy. Convection currents circulate through the star's enormous atmosphere, and subtle pulsations ripple through the outer layers, slightly altering the star's brightness over time. All of these processes are happening within a sphere of hot plasma, located hundreds of light years away. Yet despite the complexity of its internal physics, Polaris remains best known for its position in the sky rather than its structure. It marks the direction of Earth's axis. It sits near the center of the rotating heavens, and its presence has guided observers for centuries. Careful observation of Polaris over long periods revealed something unexpected. Although the star appears steady to the naked eye, precise measurements show that its brightness is not perfectly constant. The amount of light it emits changes slightly in a repeating cycle. The variation is small enough that most people would never notice it without instruments, yet the pattern is real and measurable. This behavior places Polaris in a special category of stars known as Cepheid variables. Cepheid variables are stars that brighten and dim in a regular rhythm. The changes occur because the star itself is physically expanding and contracting. The entire outer layer of the star moves outward and inward over time, altering the amount of light it emits. At first glance, it might seem surprising that a star can behave in this way. After all, stars are enormous spheres of gas held together by gravity. One might expect them to remain relatively stable once they form. However, the internal structure of certain stars makes them naturally prone to oscillations. Polaris belongs to this group. The pulsation of the Cepheid variable is not random. It follows a well-defined cycle controlled by physical processes inside the star's outer layers. To understand why this happens, it helps to imagine the star as a delicate balance between two opposing forces. Gravity constantly pulls matter inward toward the center of the star. Pressure produced by nuclear fusion pushes outward. When those forces remain perfectly balanced, this star stays stable in size. But in certain stars, particularly those in the supergiant stage like Polaris, conditions arise that cause this balance to shift periodically. The key process involves the behavior of helium in the star's outer layers. Helium exists in different states depending on temperature and pressure. At lower temperatures, helium atoms remain neutral, meaning their electrons remain attached to the nucleus. At higher temperatures, helium becomes ionized, losing one or more electrons. Ionized helium interacts with radiation in a very different way than neutral helium does. When helium becomes ionized, it absorbs and traps radiation more effectively. Energy produced inside the star cannot escape as easily, which increases the internal pressure in that layer of the star. This increase in pressure pushes the outer layers outward. As the star expands, the temperature in those layers decreases slightly. When the gas cools, helium begins to recombine with electrons and return to its neutral state. Neutral helium allows radiation to escape more freely. As energy escapes, the pressure inside the layer drops. With less outward pressure supporting the star, gravity begins pulling the outer layers inward again. The contraction compresses the gas, raising the temperature once more. Helium becomes ionized again, trapping radiation and restarting the cycle. This repeating process creates a rhythmic expansion and contraction of the star's outer layers. The phenomenon is sometimes described as the helium valve mechanism, because the ionization of helium acts like a regulator, controlling how energy moves through the star's atmosphere. When the outer layers expand, the surface area of the star increases slightly. This affects how much light the star emits, and how that light reaches observers on Earth. As the star contracts again, its brightness changes once more. The result is a repeating pattern of brightening and dimming. For Polaris, this cycle occurs over a period of a few days. The brightness variations are relatively modest compared with many other Cepheid variables, but the pattern remains consistent and detectable. Astronomers can measure these changes with sensitive photometers that track the star's light output over time. When the brightness of Polaris is plotted on a graph, the result shows a smooth wave-like pattern. Each cycle corresponds to one complete expansion and contraction of the star's outer layers. The study of Cepheid variables became extremely important in the early 20th century when astronomers realized that these stars follow a remarkable rule. The period of their pulsation is directly related to their intrinsic brightness. In simple terms, the longer the pulsation period of a Cepheid star, the more luminous that star truly is. This relationship was discovered by the astronomer Henrietta Swan Leavitt while studying Cepheid variables in the Magellanic Clouds, two small galaxies orbiting the Milky Way. Leavitt noticed that Cepheid stars with longer pulsation periods appeared brighter than those with shorter periods. Because all the stars she studied were located roughly at the same distance, the differences in brightness had to reflect real differences in luminosity. This observation led to the period luminosity relation. The rule allows astronomers to determine the true brightness of a Cepheid star simply by measuring how long it takes to complete one pulsation cycle. Once the intrinsic brightness is known, astronomers can compare it to the brightness observed from Earth. If a star appears dimmer than expected, it must be farther away. If it appears brighter, it must be closer. This technique turns Cepheid variables into cosmic distance markers. By observing Cepheid stars in distant regions of space, astronomers can estimate the distances to star clusters, galaxies, and other large structures in the universe. The method played a crucial role in one of the most important discoveries in modern astronomy. In the 1920s, the astronomer Edwin Hubble used Cepheid variables to measure the distance to the Andromeda Galaxy. His observations showed that Andromeda lies far beyond the boundaries of the Milky Way. This discovery revealed that the universe contains many galaxies rather than just one. Cepheid variables therefore helped expand our understanding of the scale of the cosmos. Polaris occupies a special place in this story. Because it lies relatively close to Earth, compared with many other Cepheid stars, Polaris serves as a useful reference for calibrating the period-luminosity relationship. Astronomers can study Polaris in great detail using telescopes and instruments that would be unable to observe more distant Cepheids with the same precision. By measuring Polaris's pulsation period and comparing it with its known distance, scientists refine the calculations used for Cepheid variables throughout the universe. In this way, the North Star contributes to measurements reaching far beyond our galaxy. Another interesting aspect of Polaris's pulsation involves changes in its amplitude over time. Historical observations suggest that the brightness variations of Polaris were once larger than they are today. During the 20th century, astronomers noticed that the amplitude of the star's pulsations gradually decreased. For a time, it appeared that Polaris might stop pulsating altogether. Later measurements revealed that the pulsations had not disappeared but had simply changed in strength. The amplitude began increasing again, suggesting that the star's internal conditions continue to evolve. These changes provide valuable clues about the internal structure of Polaris and its stage in stellar evolution. Stars passing through the Cepheid phase are undergoing significant transitions in their internal energy production and outer structure. The pulsations serve as signals from within the star, revealing how its interior responds to those changes. Observing Cepheid variables therefore allows astronomers to study both stellar physics and cosmic distances at the same time. Polaris remains especially valuable because it combines several useful characteristics. It is relatively nearby compared with most Cepheid variables, it is bright enough to observe easily, and it sits in a region of the sky that remains visible throughout the year for observers in the northern hemisphere. These qualities make Polaris one of the most accessible Cepheid stars for detailed study. Even though its brightness variations are subtle, the star's pulsations continue to provide insight into the physics of stellar oscillations. Each expansion and contraction reflects the balance between radiation pressure, gravity and ionization processes occurring deep within the star. In this sense, Polaris behaves like a slowly beating heart in the sky. The rhythm may be gentle, but it carries information about the star's internal structure and the physical laws governing stellar atmospheres. Distance is one of the most difficult things to measure in astronomy. When you look up at the night sky, every star appears as a small point of light. Some look bright, others faint, but the eye alone cannot easily tell whether a star is dim because it is small or because it lies extremely far away. Two stars might appear nearly identical from Earth, even though one is hundreds of times more luminous than the other. For early astronomers, this problem created a major obstacle. Without reliable distance measurements, it was almost impossible to determine the true scale of the universe. The stars might have been relatively nearby objects scattered around the solar system, or they might have been unimaginably distant suns spread across a vast cosmic structure. Observations alone could not immediately reveal which possibility was correct. Over time, astronomers developed a series of techniques to estimate distances in space. One of the most powerful of those techniques involves a special group of stars known as Cepheid variables. Polaris belongs to this group. Earlier we discussed how Cepheid variables pulsate, expanding and contracting in a regular rhythm that changes their brightness. At first glance, this pulsation might seem like a curiosity of stellar physics, something interesting but not necessarily useful, beyond understanding how stars behave. In reality, those rhythmic changes in brightness turned Cepheid variables into one of the most important measuring tools in astronomy. The key lies in the relationship between the pulsation period of a Cepheid and its true luminosity. Astronomers discovered that Cepheid stars with longer pulsation periods are intrinsically brighter than those with shorter periods. In other words, the time it takes for the star to complete one cycle of brightening and dimming reveals how much energy the star actually emits. This discovery created what is known as the period-luminosity relation. If an astronomer measures the pulsation period of a Cepheid variable, the relation immediately reveals the star's intrinsic luminosity. That value represents the total energy the star radiates into space. Once the intrinsic luminosity is known, determining distance becomes possible. Light spreads outward as it travels through space. The farther a light source lies from the observer, the more its light spreads out before reaching the observer's eyes or telescope. This spreading causes distant objects to appear dimmer. By comparing how bright a star truly is with how bright it appears from Earth, astronomers can calculate how far away the star must be. This technique transforms Cepheid variables into what astronomers call standard candles. A standard candle is an object whose intrinsic brightness is known. When such an object is observed at different distances, its apparent brightness changes in predictable ways. Measuring that brightness allows scientists to estimate the object's distance. Cepheid variables are particularly useful standard candles because their brightness can be determined from their pulsation period alone. Polaris, being one of the closest Cepheid stars to Earth, plays a crucial role in calibrating this method. Because Polaris lies relatively nearby, astronomers can measure its distance using parallax, a direct geometric technique that does not rely on brightness estimates. Once the distance to Polaris is known, scientists can calculate its true luminosity and confirm how it fits into the period-luminosity relation. This information strengthens the calibration of the Cepheid distance scale. In simple terms, Polaris helps astronomers verify that the mathematical relationship between pulsation period and luminosity is accurate. Once that relationship is confirmed using nearby Cepheids like Polaris, it can be applied to Cepheid variables located much farther away. The importance of this method becomes clear when we consider objects beyond our galaxy. Many distant galaxies contain Cepheid variable stars. Even though those galaxies lie millions of light years away, powerful telescopes can still detect the periodic brightening and dimming of their Cepheids. By measuring the pulsation period of those stars, astronomers determine their intrinsic brightness. Comparing that brightness with what is observed from Earth provides a reliable estimate of the galaxy's distance. This method allowed astronomers to expand the known scale of the universe. In the early 20th century, the American astronomer Edwin Hubble used Cepheid variables to measure the distance to the Andromeda Galaxy. At the time, there was an intense debate about whether certain faint spiral nebulae seen in telescopes were part of the Milky Way or separate systems entirely. Hubble observed Cepheid variables in Andromeda and calculated their distances using the period-luminosity relation. His results showed that Andromeda lay far beyond the boundaries of our own galaxy. The discovery revealed that the universe contains countless galaxies rather than a single stellar system. Cepheid variables therefore helped establish the modern picture of the cosmos. Polaris contributes to this larger effort in a quieter but equally important way. Because the North Star lies close enough for precise measurement, it serves as a nearby reference point in the cosmic distance ladder. The cosmic distance ladder is a sequence of measurement techniques that astronomers use to determine distances across progressively larger scales. At the bottom of the ladder lie geometric methods like parallax, which work only for relatively nearby stars. These measurements establish the distances to stars like Polaris. Cepheid variables form the next rung on the ladder. Once their intrinsic luminosities are calibrated using nearby examples, the method can be extended to measure distances to faraway star clusters and galaxies. Beyond that scale, other techniques such as supernova observations and redshift measurements continue the ladder outward to the edges of the observable universe. Each step relies on the accuracy of the previous one. That is why nearby Cepheid stars like Polaris are so valuable. Their well-measured properties provide a foundation for distance measurements reaching millions or even billions of light-years into space. Another advantage of Cepheid variables is their brightness. Supergiant stars like Polaris are extremely luminous compared with ordinary stars like the Sun. Their brightness allows them to be observed across vast distances with powerful telescopes. Even when located in distant galaxies, Cepheid variables can still be identified by their characteristic pulsation patterns. The predictable nature of those patterns makes them reliable indicators of distance. Astronomers can analyze the brightness curve of a Cepheid, determine its pulsation period, and immediately infer its intrinsic luminosity. Polaris's role in this system highlights an interesting contrast. To casual observers, Polaris is important because it points north. To astronomers, however, the star is valuable because it belongs to a class of objects that help measure the size of the universe. The same star that guides travelers across oceans also contributes to mapping the distances between galaxies. Studying Polaris has also revealed additional details about Cepheid variables themselves. For instance, Polaris's pulsation period has changed slightly over time. Careful monitoring of the star shows gradual shifts in the timing and amplitude of its brightness variations. These changes provide insight into how Cepheid stars evolve as they pass through different stages of stellar development. The observations help refine theoretical models of stellar structure and pulsation. In this way, Polaris serves two scientific purposes simultaneously. It anchors the geometry of the northern sky as a reference point near the celestial pole and it participates in a physical process that allows astronomers to measure the vast distances separating stars and galaxies. The quiet rhythm of Polaris's pulsation therefore carries information reaching far beyond the immediate surroundings of our solar system. Each cycle of expansion and contraction contributes to a larger effort to understand how large the universe truly is. Viewed with the naked eye, Polaris appears to be a single steady point of light in the northern sky. For centuries that was how people understood it. Navigators relied on it, travellers trusted it, and early astronomers recorded its position with great care. Nothing about the star suggested that it was anything other than a solitary object marking the direction of north. Telescopes eventually revealed a different story. Polaris is not alone. The star belongs to a small gravitational family known as a multiple star system. More specifically, it is a triple star system, meaning that 3 stars are bound together by gravity and orbit a common centre of mass. Understanding this arrangement requires a short detour into the physics of gravity. Gravity is the force that attracts objects with mass toward one another. In everyday life, we experience gravity as the force pulling us toward Earth's surface. In astronomy, gravity shapes the motion of planets, stars, and galaxies. Whenever 2 massive objects exist near each other in space, their gravitational attraction causes them to move in orbit around a shared centre. This centre is called the barycenter, or centre of mass. Even the Earth and the Sun orbit a common barycenter, although because the Sun is so much more massive, that point lies very close to the Sun's centre. In systems where the masses are more similar, the barycenter lies somewhere between the 2 objects, and both bodies move around it in noticeable orbits. Binary star systems are common examples of this behaviour. 2 stars orbit each other under the influence of their mutual gravitational attraction. In the case of Polaris, the system is slightly more complex because 3 stars are involved. The main star visible to the naked eye is known as Polaris A. This is the yellow supergiant we discussed earlier, the large and luminous star whose pulsations classify it as a Cepheid variable. Polaris A dominates the system. It is by far the brightest and most massive member. However, orbiting relatively close to it is a much smaller companion star called Polaris AB. Polaris AB is not visible without powerful telescopes, because the intense brightness of Polaris A overwhelms its faint light. For many years, astronomers suspected that such a companion existed because of subtle changes in the motion of the primary star. Careful spectroscopic observations revealed periodic shifts in the light coming from Polaris. These shifts occur because the star moves slightly toward and away from Earth as it orbits the system's centre of mass. This phenomenon is known as the Doppler effect. When an object emitting light moves toward an observer, its light waves are compressed, shifting slightly toward shorter wavelengths. When the object moves away, the waves stretch, shifting toward longer wavelengths. By analysing these shifts in Polaris's spectrum, astronomers realised that the star was not stationary. Instead, it was moving in a small orbit, influenced by the gravitational pull of an unseen companion. Eventually, with the help of advanced telescopes including the Hubble Space Telescope, astronomers succeeded in directly imaging Polaris AB. The companion star turned out to be a relatively ordinary main sequence star with a mass somewhat smaller than that of the Sun. The orbit between Polaris A and Polaris AB takes roughly 30 years to complete. During that time, the 2 stars circle their shared barycenter, while maintaining a distance comparable to the separation between the Sun and Uranus in our solar system. This orbital dance is governed entirely by gravity. The mass of Polaris A pulls on Polaris AB, while the mass of Polaris AB pulls equally on Polaris A. Both stars move in response to this mutual attraction, tracing elliptical paths around their shared centre of mass. Because Polaris A is far more massive, it moves only slightly while its smaller companion travels a wider orbit. Beyond this close pair lies another companion star known as Polaris B. Polaris B sits much farther away from the primary star than Polaris AB does. It can actually be seen through modest telescopes as a faint star located near Polaris in the sky. This star was discovered in the 18th century and was initially suspected to be merely a nearby background star unrelated to Polaris. Later measurements of its motion across the sky showed that it moves through space together with Polaris A. Both stars share the same proper motion, meaning they travel in the same direction at the same speed relative to distant background stars. This shared motion strongly indicates that Polaris B is gravitationally bound to the system. The separation between Polaris A and Polaris B is enormous compared with the inner orbit between Polaris A and Polaris AB. Polaris B lies thousands of astronomical units away from the central pair. An astronomical unit is the average distance between Earth and the Sun. At such a large separation, Polaris B takes tens of thousands of years to complete a single orbit around the system's centre of mass. The entire Polaris system therefore consists of a tight inner pair and a distant outer companion. This arrangement is not unusual in astronomy. Many multiple star systems form with hierarchical structures in which two stars orbit each other closely, while additional companions orbit much farther away. Such configurations remain stable because the outer stars move slowly enough that they do not disrupt the inner orbit. Studying the Polaris system provides astronomers with valuable information about stellar masses and gravitational dynamics. By observing how the stars move around their barycenter, scientists can calculate the masses of the individual stars using Newton's laws of motion and gravity. These measurements help refine models of stellar evolution, especially for stars like Polaris that have already expanded into the supergiant phase. The presence of companions also influences the evolution of stars in multiple systems. In some cases, stars exchange material with one another, altering their internal structure and future development. Although Polaris does not appear to be undergoing dramatic mass transfer at the moment, the gravitational interactions within the system still provide clues about how such systems form and evolve. Another interesting aspect of the Polaris system involves the motion of the stars through the Milky Way galaxy. All stars in the galaxy orbit the galactic center over hundreds of millions of years. Polaris and its companions move together through space as part of this larger galactic motion. Because the stars in the system are gravitationally bound, they share nearly identical velocities as they travel through the galaxy. This shared motion makes it easier for astronomers to confirm that the stars truly belong to the same system, rather than appearing close together by coincidence. From Earth, the Polaris system appears compressed into a tiny region of the sky. Even Polaris B, the distant companion, lies extremely close to Polaris A in angular terms. The vast physical distances between the stars become apparent only when astronomers measure their actual separation in space. Despite those separations, gravity continues to bind the system together. The concept of multiple star systems challenges the idea that stars always exist in isolation. In reality, many stars form in groups or pairs within the same collapsing clouds of gas. The gravitational interactions that follow can create complex orbital arrangements that persist for millions or billions of years. Polaris offers a relatively nearby example of such a system. Although it serves as a navigational guide and a reference point in the sky, it also participates in a quiet gravitational dance with its companions. Each star moves under the influence of the others, tracing paths determined by the laws of gravity first described by Isaac Newton. When you look at Polaris from Earth, the star appears almost perfectly fixed. Night after night it occupies nearly the same spot in the sky, quietly marking the direction of north while the rest of the heavens circle around it. For navigation and orientation, this stability has made Polaris one of the most reliable stars humans have ever used. But that apparent stillness is only a matter of perspective. Polaris is not stationary in space. In reality, it is moving through the Milky Way galaxy along with billions of other stars. The entire Polaris system drifts through the galaxy under the influence of gravity, tracing a path around the galactic center over enormous spans of time. Understanding this motion requires shifting our viewpoint from the scale of Earth and the night sky to the much larger scale of the galaxy itself. The Milky Way is a vast spiral galaxy containing hundreds of billions of stars. Our Sun resides in one of its spiral arms, roughly 26,000 light-years from the galactic centre. Polaris lies within the same general region of the galaxy, though it occupies its own location among the surrounding stars. From the perspective of the galaxy, both the Sun and Polaris are moving. Gravity from the combined mass of the Milky Way pulls stars into long orbital paths around the galactic centre. These orbits take immense periods of time to complete. The Sun, for example, requires roughly 225 million years to travel once around the galaxy. Polaris follows a similar journey. Although its exact orbit differs slightly from that of the Sun, the star moves through the same broad gravitational environment. The entire Polaris system travels around the galaxy as part of the rotating disk of stars that forms the Milky Way's spiral structure. This motion means that Polaris is not permanently positioned near the same group of neighbouring stars. Over millions of years, the star drifts gradually through the galaxy, its location relative to other stars slowly changing. Astronomers detect this motion through a measurement known as proper motion. Proper motion describes the small shift in a star's position across the sky relative to distant background objects. Because stars lie extremely far away, their movement appears very slow when viewed from Earth. Even so, precise measurements made over decades or centuries reveal that many stars gradually change position. Polaris is no exception. Although the star appears fixed on the timescale of a single night, careful observations show that it is slowly moving across the sky relative to more distant stars. This motion reflects the true movement of the Polaris system through the Milky Way. The speed of that motion is significant. Stars in our region of the galaxy typically move at velocities of hundreds of kilometers per second relative to the galactic center. These speeds may sound extraordinary, but they are necessary to maintain stable orbits within the galaxy's gravitational field. The Polaris system shares this galactic motion. As it travels, Polaris carries its companion stars with it. The gravitational bonds holding the system together ensure that the three stars move through space as a single group. While Polaris A and Polaris AB orbit each other relatively closely, Polaris B follows a much wider orbit around the pair. Yet all three stars share a common velocity through the galaxy. This shared motion is one of the reasons astronomers confirmed that Polaris B truly belongs to the system, rather than being an unrelated star located nearby in the sky. If two stars appear close together but move in completely different directions through space, they are almost certainly not gravitationally connected. In the case of Polaris B, its proper motion matches that of the primary star, confirming that the stars are travelling together. The motion of Polaris through the galaxy also contributes to changes in the appearance of the night sky over extremely long timescales. Constellations appear fixed, because the stars forming them lie so far away that their movements are barely noticeable during human lifetimes. However, those stars are not truly stationary. Each star moves along its own path through the galaxy. Given enough time, the familiar patterns of constellations slowly distort as stars shift relative to one another. This effect becomes noticeable only over tens or hundreds of thousands of years. Polaris participates in this slow transformation as well. Although the star currently lies in the constellation Ursa Minor, its motion through space will eventually alter its position relative to neighbouring stars. Future observers living thousands of years from now will see a sky that looks subtly different from ours. Constellations will still be recognisable, but their shapes will gradually evolve. This process reminds us that the night sky is not a static backdrop, but a dynamic system of moving stars. Another aspect of Polaris's galactic motion involves its origin. Astronomers believe that many stars form in clusters within large clouds of gas and dust. These stellar nurseries produce groups of stars that initially travel together through space. Over time, gravitational interactions and differences in velocity cause the cluster to disperse. The stars drift apart and become part of the broader population of the galaxy. Polaris may have formed in such a cluster millions of years ago. Evidence for this possibility comes from studies of the star's chemical composition and motion. Stars born from the same cloud of gas often share similar chemical signatures and travel through space with comparable velocities. Although the original cluster that produced Polaris may no longer exist as a recognizable group, traces of that shared origin may still be detectable. Research into stellar populations and galactic dynamics continues to explore these possibilities. Another interesting feature of Polaris's motion concerns the long-term relationship between the star and our solar system. At present, Polaris lies about 430 light-years away. This distance is large enough that the star's position relative to the Sun changes only slowly over time. However, because both the Sun and Polaris follow their own galactic orbits, their relative positions will gradually shift. Millions of years in the future, Polaris may lie much farther away from our region of space, or it may pass somewhat closer depending on the details of its orbit. The galaxy contains countless such interactions. Stars drift past one another, occasionally passing within a few light years, but rarely approaching closely enough to disrupt planetary systems. The distances between stars remain enormous, even within our local stellar neighbourhood. Polaris therefore represents just one participant in a vast gravitational system, encompassing the entire Milky Way. While it serves as a convenient marker of north from our perspective on Earth, the star itself is engaged in a much larger journey. It rotates with its companions in a triple star system. It travels with the Sun and other nearby stars around the galactic centre, and it moves gradually relative to other stars, slowly reshaping the patterns of the sky over immense stretches of time. From the ground, these motions are almost impossible to perceive directly. The night sky changes so slowly that generations of observers see essentially the same arrangement of stars. Polaris appears nearly motionless, fixed near the centre of the sky's rotation. Yet behind that calm appearance lies continuous motion on multiple scales. Earth spins beneath the sky every day. Earth's axis slowly wobbles over thousands of years. Stars shift their positions relative to one another over tens of thousands of years, and entire stellar systems orbit the centre of the galaxy over hundreds of millions of years. Polaris participates in all of these motions simultaneously. The star we see guiding travellers northward is not a static beacon. It is a massive supergiant moving through the galaxy with its companions, following the gravitational pathways that shape the structure of the Milky Way. Every star carries a history that stretches far beyond what we see when we look up at the sky. The point of light we call Polaris is only the current stage in a process that began millions of years ago and will continue for millions more. Like all stars, Polaris has changed over time, gradually transforming as the physical conditions inside it evolved. Understanding how Polaris became a yellow supergiant requires tracing the earlier stages of its life. The story begins in a cold region of interstellar space filled with gas and dust. These clouds, known as molecular clouds, are the birthplaces of stars. They contain enormous amounts of hydrogen gas, along with smaller amounts of helium and heavier elements left behind by previous generations of stars. Inside these clouds, gravity slowly pulls material together. At first, the gas may remain spread across a vast region of space, but disturbances such as nearby supernova explosions or gravitational interactions between clouds can trigger collapse. Once the collapse begins, gravity causes the gas to gather into denser clumps. As the gas contracts, it heats up. Eventually, the central region becomes hot and dense enough to form what astronomers call a protostar. At this stage, the object is not yet a true star because nuclear fusion has not begun. Instead, it is a growing sphere of gas whose internal temperature continues to rise as gravitational energy converts into heat. Polaris passed through this phase millions of years ago. Because Polaris formed with several times the mass of the Sun, the collapse that created it progressed relatively quickly. More massive stars reach the temperatures required for nuclear fusion sooner than smaller stars do. Once the core temperature climbed to about 10 million degrees Kelvin, hydrogen nuclei began fusing together to form helium. This event marked the birth of the star. When hydrogen fusion starts, The energy released produces outward pressure that counteracts the inward pull of gravity. The star reaches a stable balance known as hydrostatic equilibrium. At that moment, the star enters the main sequence phase of its life. For much of its existence, Polaris would have resembled a large, bright version of the Sun. During the main sequence stage, the star's core continuously converts hydrogen into helium through nuclear fusion. This process releases enormous amounts of energy. The energy travels outward from the core through layers of hot gas before escaping from the star's surface as light and heat. Although the star appears stable during this period, changes are gradually taking place inside the core. Every fusion reaction converts hydrogen into helium. Over time, helium accumulates in the center of the star. Because helium fusion requires much higher temperatures than hydrogen fusion, the helium core initially remains inert. The region where fusion occurs slowly shifts outward as hydrogen becomes depleted at the center. In stars with relatively small masses such as the Sun, this process continues for billions of years before the hydrogen supply runs low. In more massive stars like Polaris, the process happens far more quickly. Greater mass means stronger gravity and higher pressures in the core. Those conditions accelerate nuclear reactions, causing massive stars to consume their fuel at a faster rate. As a result, Polaris spent far less time on the main sequence than the Sun will. Eventually, the hydrogen in the central core became exhausted. When that happened, the delicate balance between gravity and pressure began to change. With no hydrogen fusion in the core to provide outward pressure, gravity caused the core to contract. As it shrank, the temperature and pressure inside the core increased dramatically. Meanwhile, hydrogen fusion continued in a shell surrounding the core. The energy produced in that shell forced the outer layers of the star to expand outward. As the star's radius increased, its surface temperature dropped slightly even while its total luminosity increased. This expansion transformed the star into a giant. Polaris eventually grew into a supergiant because of its relatively large mass. The expansion increased its radius to tens of times that of the Sun. Even though the surface cooled somewhat during this expansion, the enormous size of the star allowed it to radiate far more energy than the Sun. During this stage, the internal structure of the star became more complex. The contracting core grew hot enough to ignite helium fusion. In this reaction, helium nuclei combine to form carbon and oxygen. These reactions release additional energy, which helps support the star against gravitational collapse. Above the core, shells of hydrogen fusion continue generating energy as well. This layered structure is typical of evolved stars. Each layer contains different nuclear reactions occurring at different temperatures and pressures. The outer atmosphere of the star becomes extremely large and dynamic. Gas circulates through the star's envelope in powerful convection currents, carrying energy outward toward the surface. These internal motions contribute to the pulsations observed in Cepheid variables like Polaris. The expansion and contraction of the outer layers occur as the star adjusts to changes in energy production and pressure within its interior. Polaris currently exists within this evolving phase. Its classification as a yellow supergiant indicates that it lies between the hotter blue supergiants and the cooler red supergiants, often seen in other regions of the sky. The exact path a star follows through these stages depends strongly on its mass. Polaris has a mass estimated to be several times that of the Sun. This places it in a category of stars that evolve relatively quickly compared with smaller stars. Although millions of years may sound like an extremely long time, in astronomical terms it represents only part of the star's total lifespan. Stars much more massive than Polaris may burn through their fuel in only a few million years before ending their lives in violent supernova explosions. Less massive stars like the Sun evolve far more slowly. Polaris occupies a middle ground between those extremes. Studying stars at this stage of evolution helps astronomers understand how stellar structure changes over time. Because Polaris is relatively nearby compared with many other supergiant stars, it serves as a valuable laboratory for studying these processes in detail. Astronomers can analyze its spectrum, measure its pulsations, and observe its interactions with companion stars. Each observation reveals new information about how stars grow, expand, and evolve. Another interesting aspect of Polaris's past involves the formation of its companion stars. The entire Polaris system likely formed from the same collapsing cloud of gas and dust. During the early stages of star formation, fragments of the collapsing cloud can produce multiple stars that remain gravitationally bound. These stars begin their lives together and continue orbiting one another throughout their evolution. Although Polaris has grown into a supergiant, its companions remain smaller stars that have not yet reached such advanced stages. The presence of these companions provides astronomers with additional clues about the mass and age of the system. By studying the motion of the stars around one another, scientists can estimate how massive Polaris must be in order to produce the observed gravitational effects. This information helps refine models of stellar evolution. Even though Polaris now appears as a large, luminous supergiant, it will not remain in this stage forever. Like all stars, it will continue evolving as nuclear reactions change the composition of its core. Future stages of its life will involve further expansion, changes in temperature, and eventually the loss of outer layers into surrounding space. But those later developments belong to the future. For now, Polaris remains a bright yellow supergiant shining steadily in the northern sky. A star whose current appearance reflects millions of years of internal transformation, and that transformation continues even as the star quietly marks the direction of Earth's axis. What makes Polaris especially interesting is that its present state allows astronomers to learn not only about stellar evolution, but also about the wider structure of the universe itself. Because the pulsations of stars like Polaris provide one of the most reliable ways to measure distances across space, the North Star contributes to understanding how vast the cosmos truly is. Time operates on a very different scale when we talk about stars. Human lives last decades. Civilizations rise and fall over centuries. Even the oldest written records stretch back only a few thousand years. A star like Polaris, however, exists within a timeline measured in millions of years. The point of light that appears steady and unchanging in the night sky is actually moving through a long sequence of physical stages that began long before humans appeared and will continue long after our era has passed. Polaris today is a yellow supergiant, a star that has already evolved beyond the stable phase that most stars experience during the majority of their lives. Inside the star, nuclear reactions continue to reshape its internal structure. Gravity and pressure constantly adjust the balance of forces holding the star together. These processes will gradually push Polaris toward new stages of stellar evolution. Although nothing about Polaris seems to change quickly from our perspective, the star's future is already written in the physics of its mass and composition. Every star evolves according to the amount of mass it contains. Mass determines how strongly gravity compresses the star's core and how quickly nuclear fuel is consumed. Because Polaris has several times the mass of the Sun, it has burned through its fuel much faster than our star will. Millions of years ago, Polaris spent time as a main sequence star, steadily converting hydrogen into helium in its core. That phase ended when the supply of hydrogen at the center of the star was depleted. The star then expanded into the supergiant stage we observe today. The transformation into a supergiant dramatically increased the star's size and luminosity. Polaris now shines with thousands of times the brightness of the Sun and has a radius many times larger. But even this stage will not last forever. At present, the core of Polaris is undergoing helium fusion. Helium nuclei combine to form heavier elements such as carbon and oxygen. This reaction releases energy that helps support the star against the inward pull of gravity. Helium fusion requires much higher temperatures than hydrogen fusion, which means the core of Polaris is now much hotter and denser than it was earlier in its life. Eventually, the helium fuel in the core will also run out. When that happens, the balance between gravity and pressure will shift again. Without helium fusion to provide outward pressure, the core will begin to contract further. As the core compresses, its temperature will rise once more. New layers of nuclear reactions may ignite in shells surrounding the core, depending on the exact mass of the star. Hydrogen and helium fusion may continue in outer layers while the core becomes increasingly dense. At the same time, the outer atmosphere of the star will likely expand even farther. Many stars entering these later phases of evolution swell dramatically and cool at the surface, becoming red supergiants. In this state, the star appears cooler in colour but vastly larger in size. Whether Polaris will reach this red supergiant stage depends on the exact details of its mass and internal structure. Current models suggest that it may indeed expand further and cool, gradually shifting from a yellow supergiant into a redder and larger star. If that happens, the appearance of Polaris would change significantly for observers living in the distant future. The star would grow larger and cooler at its surface, emitting more light in the red part of the spectrum. Its brightness might increase further, though the colour visible in the sky would shift slightly toward orange or red. Even then, the changes would unfold slowly over hundreds of thousands or millions of years. From the perspective of any single human lifetime, Polaris would still appear constant. The outer layers of a supergiant star are not perfectly stable. Powerful stellar winds carry gas away from the surface, gradually reducing the star's mass. Over time, Polaris will shed some of its outer material into space. This gas will mix with the interstellar medium, enriching it with heavier elements produced during the star's lifetime. These elements, carbon, oxygen, and others, become part of the raw material from which future stars and planets will form. In this way, the life cycle of stars contributes directly to the chemical evolution of the galaxy. Eventually, Polaris will approach the final stages of its life. Stars with very large masses end their lives in dramatic supernova explosions, collapsing under gravity and rebounding in a violent release of energy. The most massive stars leave behind neutron stars or black holes. Polaris, however, is not quite massive enough to follow that exact path. Its mass places it in a category of stars expected to end their lives more gently. As the internal nuclear reactions progress and the outer layers become increasingly unstable, Polaris will likely shed much of its atmosphere into space. This expanding cloud of gas will form what astronomers call a planetary nebula. Despite the name, planetary nebulae have nothing to do with planets. Early astronomers used the term because these glowing shells of gas appeared somewhat round and planet-like when viewed through small telescopes. In reality, they are the outer envelopes of dying stars. When Polaris eventually releases its outer layers, those gases will spread outward, forming a glowing nebula illuminated by the hot core remaining at the centre. That core will become a white dwarf. A white dwarf is the compact remnant of a star that has exhausted its nuclear fuel. Although it contains roughly the same mass as the original star's core, it is compressed into an object roughly the size of Earth. The density of such an object is extraordinary. A teaspoon of white dwarf material would weigh many tons on Earth. The white dwarf left behind by Polaris will no longer produce energy through nuclear fusion. Instead, it will slowly cool over billions of years, radiating away the heat stored during the earlier stages of the star's life. Eventually, it will become a cold, dim remnant drifting through space. But that distant future lies far beyond any timescale relevant to human history. For millions of years to come, Polaris will remain a bright supergiant star, continuing its slow pulsations and guiding observers on Earth toward the northern sky. There is another aspect of Polaris's future that relates not to the star itself, but to its role as the North Star. Because of axial precession, the direction of Earth's rotational axis slowly changes over time. The north celestial pole drifts across the sky, tracing a circular path that takes about 26,000 years to complete. Polaris currently lies very close to that pole, which is why it appears almost stationary. But this alignment will not last forever. Within the next few centuries, the celestial pole will begin to drift away from Polaris. The star will no longer sit so near the centre of the sky's rotation. Eventually, another star will take over the role of the North Star. Thousands of years from now, observers on Earth will see the bright star Vega lying close to the celestial pole. Vega will become the guiding star of the northern sky while Polaris slowly moves away from that position. In this sense, the importance of Polaris as a navigational reference is temporary. The star's current alignment with Earth's axis is simply part of a long cycle, produced by the wobble of the planet's rotation. Future generations will look up at a different sky with a different pole star. Yet even when Polaris no longer serves as the North Star, the star itself will continue shining for millions of years. It will still exist as a supergiant star evolving through the final stages of its life, long after its navigational role has passed. The changes unfolding inside Polaris illustrate the broader story of stellar evolution. Stars form from clouds of gas, ignite nuclear fusion, expand into giants, and eventually shed their outer layers as their internal fuel runs out. Each stage contributes to the ongoing cycle of matter in the universe. Polaris is simply one example of that cycle. Even so, its position in the sky has given it a special significance for observers on Earth. For centuries, people have looked toward it to find direction, measure their position on the planet, and orient themselves beneath the stars. Yet when we look deeper into the physics of the star itself, we find a far more complex and evolving object than its calm appearance suggests. Polaris is not only a guide in the sky, it is a massive star undergoing slow transformation, following the same physical laws that govern the life cycles of stars throughout the universe. A single star rarely attracts scientific attention unless it possesses some unusual property. Many stars are brighter than Polaris, many are closer to Earth, others are far larger or more energetic. Yet Polaris occupies a unique position in astronomy because its usefulness extends across several different areas of science at once. The star sits at an intersection where geometry, physics, observation and history all meet. The importance of Polaris begins with something deceptively simple: orientation. Because the star lies very close to the north celestial pole, it marks the direction of Earth's rotational axis in space. This alignment creates a direct connection between the geometry of our planet and the geometry of the sky. The position of Polaris reveals how Earth is oriented at any given moment. Every star in the night sky appears to rotate around this axis as Earth spins once every 24 hours. The circular paths traced by the stars are centered on the celestial poles, and Polaris sits near the center of that rotation in the northern sky. This simple arrangement allowed observers to recognize that the sky's apparent motion reflects the rotation of Earth itself. Long before satellites or modern instruments existed, Polaris provided evidence for this relationship. By watching the stars circle around a fixed point, astronomers could deduce that Earth was turning beneath them. That realization represented a crucial step in the development of modern astronomy. The star also provided a natural reference direction for navigation. Because Polaris sits nearly due north, travellers could determine direction simply by locating it in the sky. Unlike magnetic compasses, which can be affected by local magnetic fields or variations in Earth's magnetic poles, the position of Polaris remains tied to Earth's rotational axis. This made it a reliable guide for explorers crossing oceans or deserts. However, Polaris's significance does not end with navigation. The star also plays an important role in measurements of latitude. Earlier we discussed the geometric relationship between an observer's latitude and the altitude of Polaris above the horizon. This connection arises directly from the orientation of Earth's axis. The height of Polaris above the horizon closely matches the observer's latitude in the northern hemisphere. This fact allowed early navigators to determine their position on Earth by measuring the angle between Polaris and the horizon. Instruments such as the sextant were developed specifically to measure these angles with precision. Using Polaris, sailors could maintain a constant latitude while travelling across the ocean. In this way, a star hundreds of light years away became a practical tool for mapping the surface of our planet. The usefulness of Polaris in astronomy extends even further. when we consider the star's physical properties. Unlike many stars used as navigational markers, Polaris is a Cepheid variable. Its brightness changes slightly as the star expands and contracts in a regular cycle. These pulsations are caused by physical processes occurring in the star's outer layers, particularly the interaction between radiation pressure and the ionization of helium. Although the changes in brightness are subtle, they follow a predictable pattern. The pulsation period of a Cepheid variable is directly related to its intrinsic luminosity. Stars with longer pulsation periods are intrinsically brighter than those with shorter periods. This relationship forms the basis of the Cepheid distance scale. By measuring the pulsation period of a Cepheid star, astronomers can determine how luminous the star truly is. Comparing that intrinsic brightness with how bright the star appears from Earth allows scientists to calculate the star's distance. This method turned Cepheid variables into one of the most reliable tools for measuring distances in the universe. Polaris plays a key role in this system because it lies relatively close to Earth compared with most Cepheid variables. Its distance can be measured directly using stellar parallax, which relies on geometry rather than brightness estimates. Once the distance to Polaris is known, astronomers can calculate its true luminosity and confirm how it fits into the period-luminosity relation. This calibration helps refine the Cepheid distance scale used to measure distances to other galaxies. The implications of this method are enormous. In the early 20th century, Cepheid variables allowed astronomers to determine that the spiral nebulae visible in telescopes were actually distant galaxies far beyond the Milky Way. This discovery transformed our understanding of the universe, revealing that our galaxy is only one among billions. The process that began with observing the pulsation of stars like Polaris eventually led to measurements of the expansion of the universe and the discovery that galaxies are moving away from one another. In that sense, the physics of a star in the northern sky contributed to some of the most profound discoveries in modern cosmology. Polaris also provides an excellent example of how stellar evolution unfolds. Because it is a yellow supergiant and a Cepheid variable, the star occupies a transitional phase in stellar development. Observing Polaris allows astronomers to study how stars behave when they leave the stable main sequence stage and expand into giant or supergiant phases. The pulsations of Polaris provide clues about the internal structure of the star, including the temperature, pressure, and composition of its outer layers. Astronomers use these observations to test theoretical models of stellar physics. By comparing predicted pulsation patterns with actual measurements, scientists can refine their understanding of how energy moves through stars. The fact that Polaris belongs to a triple star system adds another dimension to its importance. The gravitational interactions between the stars allow astronomers to estimate their masses by observing their orbital motion. Mass is one of the most important parameters in stellar evolution because it determines how quickly a star burns its nuclear fuel and what stages it will pass through during its lifetime. Studying the Polaris system therefore provides insight into how stars evolve under different gravitational conditions. Another reason Polaris matters in astronomy involves the stability of its position relative to Earth's axis. Because Polaris lies close to the North Celestial Pole, it serves as a reference point for measuring the orientation of Earth in space. Astronomers use observations of the pole and nearby stars to track subtle changes in Earth's rotation and orientation. These changes include axial precession, the slow wobble of Earth's axis caused by gravitational forces from the Sun and the Moon. By monitoring the position of the celestial pole relative to Polaris and other nearby stars, astronomers can measure how Earth's orientation shifts over long periods of time. Such measurements contribute to fields ranging from geophysics to satellite navigation. The star's location also makes it useful for calibrating telescopes and instruments. Because Polaris remains nearly fixed in the sky, it provides a stable target for aligning observational equipment. Many telescopes used in the Northern Hemisphere are initially aligned with the celestial pole to ensure accurate tracking of stars as Earth rotates. Polaris serves as a convenient marker for locating that pole. The combination of these roles makes Polaris far more than just a navigational star. It acts as a bridge between human observation and cosmic physics. The star helped early observers understand the rotation of Earth. It allowed navigators to determine direction and latitude. It contributed to measuring distances across the universe through the Cepheid period luminosity relation. It offers insights into stellar evolution and gravitational dynamics within multiple star systems. And it provides a reference point for studying Earth's orientation in space. Few stars serve so many purposes at once. Despite its modest brightness in the sky, Polaris has become one of the most scientifically valuable stars visible from Earth. The significance of the North Star therefore lies not only in where it appears in the sky, but also in what it allows us to learn about the universe. From the rotation of our planet to the expansion of distant galaxies, the physics connected to Polaris extends across an enormous range of scales. Understanding the star's role in these processes helps reveal why a seemingly ordinary point of light has played such an important part in astronomy for centuries, and yet, even after exploring the physics, the motion and the evolution of Polaris, there remains something quietly remarkable about the way this star appears to us from Earth. A quiet point of light has guided this entire journey. From the ground it looks simple. Polaris appears as a small star resting almost motionless in the northern sky. It does not dominate the heavens with dazzling brightness, and it rarely attracts attention from casual stargazers unless someone points it out directly. Yet over time, this modest star has revealed an extraordinary amount about the universe around us. Throughout this exploration, we began with something very familiar: the appearance of the night sky. The stars seem to drift slowly from east to west as the hours pass, tracing curved paths across the darkness. At the centre of that motion sits Polaris, appearing nearly fixed while everything else circles around it. That simple observation contains an important clue. The sky does not actually rotate around Earth. Instead, Earth rotates beneath the sky. The steady movement of the stars reflects the spinning motion of our planet around its axis. Polaris lies almost exactly along that axis, which is why it seems to remain still while the rest of the heavens sweep past. A star hundreds of light years away quietly reveals the rotation of the planet beneath our feet. Once that connection becomes clear, other patterns begin to appear. The height of Polaris above the horizon changes depending on where you stand on Earth. Observers farther north see it higher in the sky, while those closer to the equator see it sink toward the horizon. This relationship between the altitude of Polaris and latitude allowed generations of travellers to determine their position on Earth. Long before GPS satellites orbited above the planet, sailors measured the angle of Polaris above the horizon to navigate across oceans. The geometry of a distant star helped map the surface of our world, yet the alignment between Polaris and the celestial pole is not permanent. The axis of Earth slowly wobbles over thousands of years, a motion known as axial precession. Because of that gradual shift, the position of the celestial pole moves among the stars. Polaris happens to lie close to the pole today, but thousands of years ago a different star served that role, and thousands of years from now another will take its place. Even the guiding star of the north participates in the long motions of the cosmos. Looking closer at Polaris itself reveals that the star is far more complex than its calm appearance suggests. The light reaching Earth tonight left the star more than 4 centuries ago, travelling across 430 light-years of space before arriving here. Polaris is not a small star like our Sun. It is a yellow supergiant, many times larger and thousands of times more luminous. Inside that enormous sphere of hot gas, nuclear reactions convert lighter elements into heavier ones, releasing energy that powers the star's brilliant glow. The outer layers of Polaris expand and contract slightly over time, causing the star's brightness to change in a regular rhythm. These pulsations place Polaris among the Cepheid variables, a special class of stars whose brightness variations reveal their true luminosity. That discovery transformed Cepheid stars into powerful tools for measuring distance. By observing the pulsation period of stars like Polaris, astronomers can determine how luminous they really are. Comparing that intrinsic brightness with how bright the stars appear from Earth allows scientists to calculate their distance. This technique helped reveal that distant spiral nebulae were actually entire galaxies far beyond the Milky Way. The same principle now helps astronomers measure distances across the universe. In this way, the gentle pulsations of a star in the northern sky contributed to understanding the scale of the cosmos. Polaris itself is not alone. It belongs to a triple star system in which gravity binds 3 stars together. The main supergiant star is accompanied by smaller companions orbiting nearby. Their gravitational interactions allow astronomers to estimate the masses of the stars and study the dynamics of multiple star systems. Together they travel through the Milky Way galaxy, orbiting the galactic center along with billions of other stars. Although Polaris appears stationary from our viewpoint, the entire system moves through space at high speed, following the gravitational structure of the galaxy. And like every star, Polaris is evolving. Millions of years ago, it was a younger main sequence star converting hydrogen into helium in its core. Over time, its internal fuel changed, causing the star to expand into the supergiant we see today. In the distant future, Polaris will change again, shedding its outer layers and leaving behind a dense stellar remnant. Stars live out their lifetimes on timescales so long that their transformations unfold far beyond the span of human history. Yet even as Polaris evolves, its position in our sky continues to serve a special purpose. For centuries, people have looked toward it to find direction. The star has guided explorers, travelers, and astronomers. Its quiet presence helped reveal how Earth rotates, how stars evolve, and how far the universe extends beyond our galaxy. A single star, seen by millions of observers across countless generations, has provided clues about the structure of the cosmos. If you happen to step outside on a clear night and find Polaris shining in the northern sky, you will see the same steady point of light that people have relied on for hundreds of years. The star will appear calm, almost unmoving, while the rest of the heavens turn slowly around it. But behind that calm appearance lies a network of physical processes connecting the star to nearly every scale of astronomy. Polaris reflects the rotation of Earth. It reveals the geometry of latitude on our planet. It participates in the slow wobble of Earth's axis. It pulses as a Cepheid variable, helping measure distances across space. It belongs to a gravitational family of stars moving together through the Milky Way. And it continues evolving through the stages of stellar life. All of those stories are hidden within a single point of light. So the next time you look toward the northern sky and locate the North Star, remember that you are not just seeing a marker of direction. You're looking at a star whose position, motion, and internal physics have quietly helped humanity understand the structure of the universe itself. The sky will continue turning above us each night. Polaris will remain near the center of that motion for many generations, and somewhere within that slow cosmic rhythm, the star will keep shining, carrying its light across centuries of space before it finally reaches the eyes of anyone who chooses to look up.